Why is the night sky dark if the universe holds countless stars? What lies beyond the horizon of the observable universe? What secrets hide in the Big Bang's afterglow? The night sky above is quiet and dark, a serene canvas sprinkled with starlight. In the stillness of midnight, you gaze upward and feel almost a hush from the cosmos. Each star twinkles in silence, separated by unfathomable distances, their light taking ages to reach your eyes. Yet despite the countless stars, the sky between them remains black and empty. The silence and darkness make you wonder, in a universe so vast, why does the night feel so quiet? What secrets hide in the dark gaps between the stars? Under the hush of night, you might expect a chorus of cosmic noise or endless light, but instead, there is a gentle stillness. Long ago, people looked up and asked why the darkness dominates if an infinity of stars is out there. If space goes on forever, with stars everywhere, shouldn't the sky blaze bright even at midnight? The darkness itself became a riddle, a puzzle hinting that perhaps the universe is not infinite in the way it once was imagined. This quiet darkness is not empty at all. It's full of questions and subtle clues. As you stand under the sky's dome, you can't help but sense something profound. The tranquil darkness holds a larger question. How far does this universe extend, and what lies beyond the veil of what we can see? Each pinpoint of starlight is a messenger from afar, an echo from distant realms. They travel immense expanses just to reach us, hinting at a cosmos far larger than our earthbound perspective. And in between those pinpoint beacons stretches a silent void, a void that might not be truly empty, but rather beyond our current reach. In the silence, your thoughts drift. Could there be more out there? Perhaps faint signals or whispers that our ears can't hear and our eyes can't see. The universe feels like a grand, enigmatic stage set with tiny lights, but mostly curtain. Gazing into this darkness, you realize you are peering into deep time and space. The starlight is ancient, the darkness even older. It's as if the cosmos is telling a story in faint, scattered verses. We catch only snippets, starlight here, a galaxy's glow there, and everything else is a mystery, perhaps a promise of more to come. This calm, dark expanse makes the mind wander. It stirs a gentle curiosity that is as vast as the sky itself. In that curiosity lies the larger question, echoing from the void. Are we glimpsing only a small part of a much greater cosmos? The quiet sky invites you to listen closely. Maybe, hidden in its apparent silence, the universe is whispering. Perhaps in that whisper is an invitation to seek out what lies beyond the darkness we see, to find the mysterious signals from deep space that travel in silence, waiting to be heard. With that thought, the journey begins, moving from the simple beauty of a quiet night into the profound mysteries that the darkness holds. Imagine for a moment that the universe has an edge, not a physical wall you could touch, but a limit to how far you can see. This is not because space ends there, but because light has only had so long to travel. We call this limit the observable universe, the bubble of space and time from which light has reached us since the cosmic dawn. Beyond it, there may be more galaxies, more space, perhaps an infinity of creation, but their light has not yet arrived. The observable universe is like living in a softly lit clearing surrounded by deep mist. We see what the light has revealed, and beyond that lies a shrouded unknown. The stars and galaxies we observe mark the extent of this cosmic horizon. They stretch out in every direction, farther and farther, until they fade into a dim haze. The most distant light we can catch comes from when the universe was very young, a time long before galaxies even existed. Back then, everything was a glowing fog of energy and particles. As the universe expanded and cooled, that hot glow faded to a whisper of microwaves, a gentle afterglow filling the sky. We call it the cosmic microwave background, a faint signal that bathes the entire sky. It comes from all around us, about as far back as we can look. This ancient light is like the pale light of dawn after a long night, the moment the universe became transparent and let illumination free. Standing here on Earth, at the center of our observable sphere, we peer out as far as those primordial whispers of light. Current estimates say this horizon is around 46 billion light-years away in every direction, a sphere of staggering size. This number is almost beyond comprehension. Each light-year is about 6 trillion miles, and we're talking billions of those. And yet, that enormous span is not the whole universe, only the part we can currently see. Beyond that horizon line, space likely continues, perhaps endlessly. The galaxies don't abruptly stop at our sight's edge. They continue in darkness, beyond our reach. Think of it like looking out across a vast ocean at night. You see the circle of sea touched by moonlight around you. But beyond the dark horizon, the ocean continues unseen. Just so, our cosmic ocean likely extends far beyond the visible waves of light that reach our eyes. The observable universe is our cosmic horizon, the edge of the knowable. It's a reminder of both the power and the limits of our perception. We can map countless galaxies within this enormous bubble, but we must humbly acknowledge that there is a frontier beyond which we cannot yet witness anything at all. And so, as we contemplate this border of sight, a gentle wonder stirs. What lies just out of view, in realms whose light has not yet arrived? The quiet dark beyond the horizon isn't empty or void of stars. It's simply territory unreached by any signal we've had time to receive. With each passing year, the boundary shifts outward ever so slightly, as new light travels across the vast distances to finally greet our telescopes. But even with time, there will always remain a beyond, a region forever hidden if the universe is truly infinite, or if it expands faster than light can bridge. This realization, that we live confined to a vast but finite visible sphere, sets the stage for deeper questions. We find ourselves yearning to peer further, to know what cosmic wonders exist outside this cosmic horizon. What mysteries might dwell beyond the edges of sight, and how could their presence influence the piece of the universe we can see? It's humbling to realize that much of the universe is hidden from us, simply because light has not had time to arrive. This isn't just a quirk of distance. It's woven into the fabric of space and time. In physics, we speak of light cones, a way to imagine what events in the universe can ever affect one another. Think of a light cone like the glow of a lantern in a dark space. Only things within that glow can be seen or felt. For us, at this moment, only events within our past light cone, that is, events from which light or any signal has had time to reach us, can influence what we observe. Anything outside that sphere of influence is, for now, completely beyond our touch, hidden in darkness, not because it isn't there, but because its light hasn't arrived. No matter how powerful our telescopes, we are fundamentally limited by this cosmic speed limit. Light is swift, but the universe is vast and young. There hasn't been enough time since the beginning for light to cross the entire expanse, if that expanse is truly enormous. We gaze as far as possible, but beyond a certain boundary, it's as if a curtain is drawn. We know nothing of what lies behind it, not because it's empty, but because those regions are outside our light cone. They're simply too far for their light to have reached us in the age of the universe. You might wonder, if we just wait long enough, will more of the universe come into view? In a sense, yes. As time flows onward, light from slightly more distant realms will trickle in and broaden our horizon. The observable universe slowly grows as new stars' light finally makes its journey into our sight. But here's a twist. While we're waiting, the universe is not sitting still. Space itself is stretching and expanding. Distant galaxies are drifting, carried by the swelling fabric of spacetime. In fact, some galaxies are being pushed away so swiftly by expansion that their light can never catch up to us. Even as light struggles to traverse the gulf, the space in between grows and carries those galaxies farther out of reach. This means there are limits, not just in the past, but in the future too. There may be galaxies forever beyond our ability to see, no matter how time passes or how we improve our technology. It's as if we live in a vast cosmic bubble where outside events continue to unfold, but their story will never be heard by us. The universe could be teeming with wonders, galaxies, stars, perhaps even other forms of life, beyond that unreachable horizon, and we would never know, not directly. This realization is both awe-inspiring and slightly melancholy, a recognition that the cosmos is larger than what we can observe, perhaps in a way infinitely larger. The boundary defined by our light cone is a fundamental horizon of knowledge. It reminds us of our place in time. We are observers in a young universe, limited by the speed of light, witnesses to only a portion of creation. But human curiosity doesn't stop at the edge of sight. We can't see these hidden regions, yet we can imagine them and seek indirect clues of their existence. Why is the universe beyond our view relevant to us? Because understanding the whole story might help explain the part we can see. And so we turn to theory and inference, using what we know as a guide to what lies in the cosmic dark beyond our light cone. To truly grasp the universe's vastness and answer that larger question, we must explore ideas that extend our reach beyond direct observation. We ask, might there be subtle footprints or echoes from those unseen regions imprinted on the piece of the universe we can see? Are there hints in the patterns of galaxies or in the faint afterglow of the Big Bang that tell us about the wider cosmos? These questions guide us onward. If we can't travel beyond the cosmic horizon in space, perhaps we can in understanding. Our journey now turns to the early universe itself, searching for clues in its first moments that could illuminate what lies beyond the borders of sight. To uncover the hidden cosmos, we must roll back time to when the universe itself was new. In the beginning, as far as our best theories tell us, the universe was born in a hot, dense flash, an event we call the Big Bang. Everything we see today, all the galaxies and stars, were once compressed into an unimaginably small and energetic state. As the universe expanded and cooled from that initial fireball, light finally broke free and the cosmic dawn arrived. That first light, now stretched into a faint microwave glow, still lingers around us as the cosmic microwave background. But when scientists studied this primordial light, they stumbled upon a curious puzzle. No matter which direction you look, this afterglow has nearly the same temperature. Opposite sides of the sky, separated by vast distances, appear almost identical in their early conditions. How could that be, if there wasn't enough time since the Big Bang for light, or heat, or information to travel between those far-flung regions? It was as if the universe had started out too uniform, too synchronized, across expanses that seemingly could never have communicated with each other under normal expansion. This conundrum is known as the horizon problem. Without a solution, it's like finding two people on opposite ends of the world who spontaneously started singing the same tune without ever meeting or hearing one another. It hinted that something was missing in our story of the early cosmos, a mechanism that could connect distant parts of the young universe, allowing them to share information and reach a common temperature and structure. The answer that emerged was bold and fascinating. In the split-second infancy of the universe, space itself might have undergone an unbelievable growth spurt. We call this idea cosmic inflation. In a fraction of a second, the universe could have expanded exponentially, doubling in size again and again at a pace that makes the current expansion look gentle. This was a faster dawn, a moment when the cosmos grew far, far beyond its initial microscopic size in the blink of an eye. Because of this rapid expansion, regions that are now on opposite sides of our observable universe could once have been snug neighbours, intimately connected before inflation blew them apart. Like ink droplets on a balloon that suddenly inflates, points that were once close become vastly separated. Inflation wasn't just fast, it was beyond imagination, outpacing even the speed of light. Normally, nothing can move through space faster than light, but inflation was different. It was space itself expanding. By ballooning space so dramatically, inflation could carry regions apart quicker than light could travel between them. This extraordinary growth spurt would mean that before inflation, the whole region that became our observable universe was much smaller, perhaps small enough that it had time to even out its temperature and conditions. Then, when inflation occurred, that region was stretched out to encompass everything we now see and more, explaining why the distant corners of our cosmic horizon look so similar. This concept of inflation did more than solve the horizon problem. It also helped to explain other mysteries, like why space today appears so remarkably flat and not curved in on itself, as well as why we don't see certain exotic relics that might have been expected from a Big Bang without inflation. In essence, inflation set the initial stage for the universe we observe. Smooth on large scales, almost uniform, but with tiny imperfections, and vast beyond reckoning. It was the cosmos giving itself a head start, smoothing out wrinkles and spreading out far and wide in its earliest moments. Imagining this can leave you in quiet awe, a tiny fraction of a second that shaped all the eons to come. From our perspective now, billions of years later, inflation is like a brief flash of miraculous expansion, so short we cannot directly witness it, yet its fingerprints are subtly imprinted everywhere we look. We see its legacy in the uniform glow of the early universe and in the very structure of the cosmos. Inflation was the universe's rapid awakening, a crucial chapter where our cosmic story finds the necessary plot twist to make sense of the harmony we see across the sky. Having introduced this faster dawn, we realize something intriguing. If inflation really happened, it might have done more than just smooth out our patch of the universe. What if that tremendous expansion carried on beyond our view, or happened in other places too? The idea of inflation opens the door to possibilities far greater than just our observable bubble. But before we venture into those speculative realms, let's consider one more gift. inflation may have given us, the seeds of structure that would later grow into galaxies and stars. Even in the smoothness, there were tiny irregularities, like faint whispers in a quiet room, that would eventually lead to everything we find familiar in the cosmos. Our journey continues into those subtle beginnings, looking at how the cosmos turns simplicity into the rich tapestry of stars and galaxies we see today. In the aftermath of that wild inflationary surge, the young universe was almost eerily smooth. Inflation blew up any clumps or irregularities, leaving space nearly uniform in all directions. Yet, it wasn't perfectly featureless. Hidden in the smoothness were minute differences, tiny fluctuations in density and energy, so small as to be barely there. These were the quantum ripples, the faint imprints of chance and uncertainty writ across the fabric of the newborn cosmos. During inflation's brief moment, even the infinitesimal jitter of quantum particles got stretched to astronomical scales. Much like the way a quiet whisper can echo across a vast, empty cathedral, these microscopic fluctuations were magnified to cosmic proportions. Imagine the vacuum of space at the smallest scale, alive with subtle vibrations, particles flickering in and out of existence as quantum physics allows. Normally, such ephemeral flickers average out to nothing noticeable, but when inflation rapidly swelled the universe, it froze some of these tiny variations into the fabric of space itself. Suddenly, regions that were ever so slightly denser or cooler, by sheer randomness, became etched into the expanding cosmos. They were the seeds, the first gentle variations in an otherwise smooth ocean of matter and light. As the universe continued to expand and inflation ended, these seeds of structure began to grow. Gravity, the tireless sculptor, started to amplify the differences. In places where there was a touch more matter, gravity pulled in even more material over time. Those regions grew gradually denser. Gas gathered and eventually ignited to form stars, clusters of stars bound together as galaxies, and clusters of galaxies forming vast filaments and walls in space. In places that had a touch less matter, material drifted away, leaving voids, great dark gaps between the galaxies. The universe became a grand cosmic tapestry woven from these threads of density, all tracing back to those minuscule quantum ripples. It's astonishing to think that every galaxy, every star, perhaps every planet, owes its existence to tiny quantum whispers in the first moments of time. The majestic Milky Way arching across the sky, the swirling grandeur of distant galaxies photographed by our telescopes. All of it can be traced back to slight unevenness in the primordial soup. Those quantum fluctuations were like the first random notes of a melody that inflation amplified, and gravity later orchestrated into the complex symphony of the cosmos we observe today. We have evidence of these ancient ripples preserved in the light of the cosmic microwave background. When we map that faint afterglow with sensitive instruments, we see it isn't perfectly uniform after all. There are faint patches, slightly warmer or cooler by only a few dozen millionths of a degree. Those subtle patterns are the direct imprint of the seeds of structure. They're an image of the universe as a baby, a picture of the almost smooth cosmos with just the tiniest freckles. And those freckles grew up to be galaxies and clusters. So from the silence of a uniform cosmos, inflation's end left a quiet pattern, a whisper of randomness that later shouted out into all the structure around us. It's a beautiful thought. Out of something so subtle and random arose the grand design of stars and galaxies. The cosmos took quantum chance and made it into something concrete. But this leads us to yet another mystery. If the initial conditions of the universe were set by this mix of inflation and quantum fluctuation. Why were those conditions just right for life to eventually emerge? We see that the universe's structure had to start somewhere, and it did so with these tiny ripples. Yet as the cosmos evolved, it followed very particular pathways. The next question arises: did everything have to be exactly as it is for us to be here pondering it? Or are there coincidences in those cosmic parameters that beg for an explanation? As we continue, we'll reflect on how finely tuned our universe seems to be, and what that might imply about the broader reality beyond what we can directly observe. As we look closer at the story of our universe, we start noticing uncanny coincidences. Certain properties of the cosmos seem to be just right, as if finely tuned to allow the existence of galaxies, stars, and eventually life. These are often called the fine-tuning puzzles. They are the delicate balances and precise values that make our universe the way it is, and they whisper of deep mysteries. Why, for instance, is the force of gravity so perfectly balanced with the expansion of the universe? In the early universe, gravity tried to pull everything back together, while the initial expansion from the Big Bang tried to push everything apart. If the expansion had been even a little stronger, the universe might have spread out too fast for stars and galaxies to form. Matter would have thinned into a cold mist, life never gathering a foothold. If the expansion had been a touch weaker, gravity might have quickly halted the expansion and caused the universe to recollapse in a hot, big crunch, ending the cosmic story almost as soon as it began. But somehow, expansion and gravity were in near-perfect balance, setting the stage for a long, stable, cosmic evolution. Gravity's strength itself is another quiet oddity. It's an incredibly weak force on the scale of subatomic particles, far weaker than the other fundamental forces. Yet, with enough mass, gravity becomes dominant over large distances, pulling together stars and galaxies. If gravity were significantly stronger as a fundamental force, stars might burn faster and hotter, consuming their fuel in the blink of cosmic time, or collapsing into black holes too easily. Planets might not find gentle, life-friendly orbits. If gravity were much weaker, stars might never ignite at all, or galaxies might not hold together, leaving the universe a diffuse sea of gas with no shining lights. Our existence relies on gravity being just this very peculiar Goldilocks strength, not too strong, not too weak. Then there's the precise recipe of the early universe. The initial mix of matter and energy, the slight irregularities seeded by inflation, even the amount of dark matter and dark energy, all had to fall within certain ranges to produce the cosmos we know. The tiny fluctuations from Chapter 5, those 1 in 100,000 differences, had to be of just the right size. A bit smaller, and the universe would remain nearly featureless gas. A bit larger, and everything might have collapsed into dense clumps or black holes early on. The cosmos walked a fine line. Even the amount of matter compared to antimatter in the very beginning had to be just a hair off perfect symmetry, just enough that a bit of matter was left over to form all the galaxies, after most of it annihilated away. Why that tiny excess? It's another whisper of a coincidence that allowed us to exist. Perhaps one of the most striking fine-tuning mysteries involves something called the cosmological constant, which is essentially the energy of empty space, the thing driving the universe's accelerated expansion today. The value of this energy is astoundingly small, almost zero, yet not exactly zero. If it were much larger, the universe would have blown itself apart long before galaxies or stars could form, a runaway expansion overwhelming gravity completely. If it were negative or much smaller, perhaps the expansion would never accelerate, and other issues might arise. the number is puzzlingly tiny and precise, raising eyebrows among scientists. It feels like the universe, out of countless possibilities, landed on just the right numbers for complexity to blossom. Each of these examples is like a coin that happened to land on its edge. Improbable, and yet here we are, witnessing the result. We collect these whispers of coincidence, the balanced expansion, the force strengths, the particle ratios, the energy in empty space, one after another. Any small change in these, and the story might have been very different, with no observers around to notice the difference. It's as if the universe had a recipe, and somehow it followed it to the letter, ensuring the cosmic cake would rise just so, that stars would shine and chemistry would unfold into life. To some, these fine-tuned parameters hint at meaning or purpose. To others, they cry out for an explanation rooted in science, a deeper principle that made them inevitable, or a multiverse where many different outcomes occur, and we just happen to be in one that works. It's a gentle mystery, not screaming for attention, but persistently nagging at our understanding. How did our universe get these just right conditions? Was it pure chance? Something inescapable? Or something else entirely? As we ponder these questions, we feel the need to widen our perspective even more. Perhaps our universe isn't the only roll of the dice. Maybe there are countless universes, each with different settings, and naturally we find ourselves in one of the rare few that could harbour observers asking these very questions. This line of thought leads us to the anthropic hints, the idea that our existence might itself select the kind of universe we observe. In the next part of our journey, we explore this intriguing concept, looking at how the vast ensemble of possibilities could contain many worlds, and how we, as living beings, perceive only the subset that welcomes life. The notion that our universe seems tailored for life leads to a profound contemplation. What if our universe is not the only one? Perhaps the apparent fine-tuning isn't by grand design or sheer improbable luck, but rather the result of a simple fact. Out of a vast diversity of worlds, we inevitably find ourselves in one of the rare universes where conditions allow observers to exist. This idea is encapsulated in what's known as the anthropic principle. In essence, it says that the universe we observe must be compatible with our existence within it, because if it weren't, we simply wouldn't be here to observe it. It sounds almost tautological, but it carries a subtle hint. Maybe many universes exist with many different characteristics, and only in a subset of them do stars, planets, and life arise. We, as observers, would naturally be in that habitable subset. Imagine an expansive library filled with books. Each book represents a universe, each with a different story governed by different physical laws or initial conditions. Many of those books might be unreadable or boring, universes where nothing interesting happens, no life forms to read the story. Some might be brief flickers that end almost as soon as they begin. Others might expand forever, but never form anything more than diffuse gas. We happen to pull a book off the shelf that has a rich, complex story, our universe with galaxies, stars, and life. We might marvel at how perfect the plot seems, but if the library is vast enough, maybe it was inevitable that some book somewhere had a storyline that allowed beings like us to come forth and marvel at it. In all the other books where conditions weren't right, no one is there to be disappointed that the story never developed. The anthropic principle comes in a couple of forms. The weak anthropic principle simply observes that we can only find ourselves in a universe capable of supporting life. So we shouldn't be surprised that we observe precisely such conditions. It's like saying it's no coincidence that Earth has breathable air and liquid water when we consider we evolved here. If it didn't, we wouldn't be here to notice. The strong anthropic principle, a more speculative idea, suggests that perhaps the universe's laws must allow for life at some point, implying some deeper reason or necessity for life's emergence. Many scientists stick with the simpler, weak version. Given a large ensemble of possible universes or domains with varying properties, it's natural that at least one would have the right combination for life, and that's the one we find ourselves in. This concept can feel both empowering and a bit disquieting. It means on one hand that maybe we shouldn't be so shocked by the fine-tuning. If countless cosmic dice are rolled, eventually a winning combination comes up, and we simply are living in the universe where it did. On the other hand, it suggests something grander, a possible multiverse, a vast collection of realms beyond our own, most forever inaccessible to us. We only see our tiny cosmic bubble with its particular laws of nature, but there could be countless other bubbles, each with different laws or constants. It's a humbling thought that what we've been calling the universe might just be a small part of an unimaginably larger and more varied whole. The anthropic perspective invites us to consider ourselves not as a central focus of a universe fine-tuned for us, but rather as lucky inhabitants of a universe that happens, by chance, to permit our existence. It's a shift from seeing purpose to recognizing a kind of cosmic selection bias. Of course, this idea isn't proof of anything by itself. It's a way to make sense of the coincidences without invoking something mystical. It hints that to answer the fine-tuning puzzles, we might need to think beyond a single universe. Perhaps nature tried every possible variation in an ever-expanding multiverse, and we are in one corner where everything lined up just so. If this is true, then those mysterious coincidences we noted aren't really coincidences at all. They're necessities from our point of view. We see them precisely because only where they hold true could we be around to wonder about them. Still, such a multiverse concept begs more questions. How could multiple universes come to be? What mechanism would create this grand ensemble of realities? To explore that, we turn back to our earlier idea of inflation. The theory that gave our universe its head start might also hold the key to generating a plethora of universes, an eternal inflation that never completely ends, spawning new big bangs beyond our horizon again and again. This next idea takes us further into the speculative, yet tantalizingly possible realm of a cosmic landscape far beyond our own sky. Inflation, the dramatic opening chapter of our universe, may not have been a one-time event. The idea of eternal inflation suggests that the rapid expansion of space wasn't limited to our patch of the cosmos. Instead, inflation could be an ongoing process, still happening in far-flung regions beyond our observable horizon. In this scenario, what we think of as the universe is just one bubble that formed when inflation ended in our region, allowing particles and galaxies to coalesce. But elsewhere, outside our bubble, inflation might continue to blow space up at a furious rate, and now and then, other bubbles nucleate, each bubble a baby universe in its own right, with its own big bang, its own expansion and evolution, and perhaps its own distinct laws of physics. Picture a vast, endless ocean of space that is inflating forever, a foam of bubbles forming within it. Each bubble is a cosmos, and ours is just one such bubble. We peer out at 46 billion light-years in every direction and see the limits of our bubble. Beyond it, we can't observe directly, but eternal inflation paints a picture of a much larger reality. Most of that reality is still inflating, out of reach, but constantly sprouting new universes. It's a grand cosmic bubble bath, where creation is not a singular event, but a continuous, eternal process. In some bubbles, the physical constants might be different. Perhaps gravity is a bit stronger in one, or the proton a bit heavier in another, resulting in very different kinds of worlds. In others, maybe stars and galaxies form much like our own. The multiverse, born from eternal inflation, could encompass every possibility. This concept provides an elegant context for the anthropic ideas we explored. If there are countless bubbles, each with random characteristics, it's no surprise that one of them has the right conditions for life. We're simply in that lucky bubble. Eternal inflation offers a mechanism for that vast ensemble, a natural way to generate diverse universes without needing a separate trigger for each. Once inflation starts, it never completely stops. It ends in patches, forming bubbles like ours, but continues elsewhere, ensuring an infinite brood of universes over time. It's a breathtaking idea, almost intoxicating to contemplate. And while it stretches our imagination to the limit, it's not pure fantasy. It arises from equations and theories intended to explain the universe we do see. Eternal inflation is a logical extension of inflation itself. The same mathematics that can solve the horizon problem and explain quantum fluctuations has solutions that imply inflation could be eternal into the future, and that new big bangs could be spawning beyond our view. Have we caught any evidence of these other bubbles? This is a challenging question. By definition, other universes lie outside our observable realm, so direct observation is nearly impossible. But scientists have pondered if a neighboring bubble universe could have, in the very distant past, collided with our own bubble. If such a cosmic fender bender occurred, it might have left subtle fingerprints in the cosmic microwave background, the faint echo of our own Big Bang. Researchers have actually searched maps of that ancient light for unusual circular patterns or hotspots that could hint at a collision with something beyond, something elsewhere. So far, no clear sign has emerged. The evidence remains elusive or ambiguous. That isn't surprising, given how faint and rare such signals might be. If another bubble never collided with ours in an observable way, we might simply see nothing at all of the others, and they would remain purely theoretical. Yet, the very plausibility of a multiverse gives a kind of first glimpse of elsewhere through our understanding. It expands the mind's eye to see our universe as just one part of a much larger cosmic puzzle. We begin to interpret the silence beyond our horizon, not as emptiness, but as the hush where countless other verses of the cosmic symphony play out beyond earshot. The mysterious signals we do detect, the uniformity of the cosmic background, the tiny fluctuations, the unexpected balances in nature's constants, can be seen as indirect whispers of that greater multiverse. They hint that our reality might be a small island in a vast, strange archipelago of universes. Entertaining the idea of eternal inflation and a multiverse encourages humility. We might never empirically confirm these other universes, yet their possibility shapes how we think about everything. We've moved from asking what lies beyond the stars, to what lies beyond the observable universe, to what lies beyond even our universe's laws. It's a journey that takes our quest for knowledge to the brink of metaphysics, yet remains grounded in the attempt to solve real cosmological mysteries. And it leaves us gazing at the night sky differently, seeing it not just as a boundary of our universe, but perhaps as a tiny window into an incomparably larger existence. Now, as our exploration draws toward a close, we reflect on how far we've travelled in thought. We began with a quiet night sky and simple wonder, We end with a vision of potentially infinite cosmic diversity. But even as we cast our imagination into these vast possibilities, we remain anchored here, in our own bubble universe, trying to piece together a coherent picture. What we have now is not a final answer, but a new perspective, a map of questions as much as answers, for the journey ahead. Standing here at the end of our journey, we find ourselves holding a new kind of map. It isn't a map with continents or stars drawn on paper, but a mental map of the vastness that surrounds us and the mysteries it holds. We began with a simple wonder under a quiet sky, and step by step ventured deeper into the cosmic ocean. Along the way, we marked some important landmarks on this map of understanding. The horizon of what we can see, the inflationary burst that set everything in motion, the tiny quantum seeds that grew into galaxies, the delicate coincidences that make our universe hospitable, and the tantalizing idea that our universe might be just one island in a boundless sea of universes. This map is far from complete. In fact, with each discovery, it has shown us more uncharted territory. Every answer we found opened up new questions. We solved the riddle of why the night is dark, only to reveal the enormity beyond our observable horizon. We traced how our universe came to look as it does, only to face the puzzle of why its laws allow us to exist at all. We entertained an explanation for that puzzle, only to find ourselves contemplating infinite realms beyond our own. Our map of the cosmos expanded dramatically, but with each expansion, the frontier grew too. There is always a beyond at the edge of our understanding, a region on the map still labelled with that old phrase, "Here be the unknown." What lies ahead as we continue to explore? Perhaps new instruments and experiments will let us peer further into space and time, or detect faint whispers from the early universe that we've only imagined so far. We might catch the subtle ripples of gravitational waves from the universe's first moments, carrying messages about how inflation played out. We might refine our observations of the cosmic microwave background, uncovering new clues that either bolster the idea of inflation and a multiverse, or reveal surprises that send us back to the drawing board. We could discover new particles or phenomena that hint at dimensions or universes beyond our own. It's also possible that some questions will remain unanswered, not for lack of curiosity, but because of fundamental limits. We may find that a multiverse, if it exists, leaves no trace we can detect from our cosmic vantage point. If so, our journey ahead will involve finding meaning in understanding the universe we can see, while accepting that some truths might remain just out of reach. Even if we never see beyond our cosmic horizon, the very notion that beyond exists has changed us. It reminds us that reality is deeper and more expansive than what our senses alone reveal. This brings about a gentle sense of cosmic humility. We realize that we are part of an immense tapestry, one thread in a vast cosmic cloth. The quiet night sky that we started with is no longer just a static backdrop. It has become a gateway to grand questions and profound ideas. When you look up now, perhaps you'll feel the layers of mystery hidden in that darkness. Each star becomes more meaningful. Not only is it a distant sun, but also a clue to the galaxy it belongs to. Each galaxy, in turn, is just one among countless others shimmering within our observable domain. And beyond that domain, there may lie an unending expanse of further galaxies and universes, silent to our ears, but real in their own right. Rather than making us feel insignificant, this expanded perspective can be oddly comforting and inspiring. It tells us that the cosmos, perhaps the multiverse, is rich with possibilities, and that our quest for understanding will likely go on without end. There will always be new horizons to explore, new mysteries to probe. There will always be more echoes from the void to listen for. Each discovery we make is like learning a new constellation in the sky of knowledge, helping us navigate a little further into the unknown. We find that the more we learn, the more we realize remains to be discovered, and that is a beautiful thing. As we gently conclude this part of our journey, the night remains as tranquil as ever. The stars still sprinkle the sky, distant and indifferent and beautiful. The big questions we've pondered are still out there, lingering without final answers. But that's all right. We have traced some of the paths and possibilities on our map of the great unknown. We have listened to faint cosmic echoes and recognized them as hints of something more. In the stillness of space, we've found a story that connects the tiny flicker of quantum events to the sweep of countless galaxies, linking our small world to a vast cosmos and maybe even to realms beyond. The journey ahead is open-ended, truly an invitation rather than a conclusion. Whenever you find yourself under a silent, starry sky, you can feel that invitation. Let yourself be aware that in that darkness above, there are whispers of creation, mysterious signals traveling across the ages. They carry the secrets of what was, what is, and perhaps what might be. And as long as the spark of curiosity lives within us, we will keep listening to those quiet echoes. We'll follow them into the unknown, letting them guide us gently through the cosmic dark, ever onward on this grand adventure of understanding our reality. Over the course of our journey through various multiverse ideas, a pattern emerges. Each concept has elements grounded in well-established physics or mathematics, yet each extends beyond the proven into the speculative. We find that while some multiverse propositions are closely tied to accepted science, others venture into more uncertain territory. It's useful to take stock of what are genuine clues and what remain mere claims or hypotheses for each level of the multiverse we've discussed. In other words, let's distinguish which parts of this puzzle have supporting evidence and which remain largely conjectural. For level 1, the idea of a universe beyond our cosmic horizon, we have something close to a near certainty rather than a wild speculation. The notion that space extends beyond what we can see is strongly supported by the observed uniformity and geometry of the universe. We have no evidence of an edge or boundary. Everything we see suggests that conditions continue beyond our horizon. This is essentially an extrapolation of known cosmology rather than a leap of faith. While we can't directly observe beyond our light horizon, the simplest assumption is that the same physical reality we see around us persists outward indefinitely. In science, when a model works and shows no signs of breakdown, we assume it continues to hold. And that's the case with level 1. So, in this instance, many scientists would say it's more than a claim. It's a reasonable inference. The clue supporting it is simply the continuity and smoothness of the cosmos we observe. Since we don't observe any strange cutoff at the limits of our vision, it's sensible to believe the universe carries on beyond, perhaps infinitely. In the case of level 2, the inflationary bubble universes, we find partial clues interwoven with speculation. The motivation for bubble universes comes from the theory of inflation, which itself has strong evidence in our universe. The uniform temperature of the cosmic microwave background and the distribution of galaxies both point to an early era of rapid expansion. If inflation happened here, and if the underlying physics allows inflation to continue elsewhere, it would naturally produce other pocket universes. The clues here are indirect. The success of the inflation theory makes a multiverse of bubbles plausible, even perhaps likely, in a mathematical sense. But we must emphasize that we have not actually seen any other bubble. All evidence for them is circumstantial. It's the if inflation, then maybe multiverse line of reasoning. So, level 2 stands on a mix of solid ground, inflation is well supported for our universe, and conjecture that inflation produces a multitude of universes with varying properties. It's a strong theoretical claim in search of empirical evidence. A potential clue, as we've explored, would be a detected collision or some remnant of another bubble's influence, but none has been confirmed so far. Without such a clue, the bubble multiverse remains an enticing hypothesis, grounded in what we think our cosmic history implies, yet ultimately unverified. For level 3, the many worlds interpretation of quantum mechanics, the situation is intriguing, but lacking direct evidence. The idea is fully consistent with quantum theory, as confirmed by experiments. In fact, no test to date contradicts many worlds or uniquely supports an alternative. Quantum mechanics gives the same predictions either way. Many worlds introduces no new physics. It simply offers a different narrative for quantum events. The clue here is quantum superposition itself. Particles seem to be in multiple states until observed. Many worlds takes that at face value, saying the particle is in all states in separate branches of reality. It's an elegant way to remove the arbitrariness of the so-called collapse postulate. However, treating those branches as actual separate universes is the speculative leap. We have no way to peek into other branches once decoherence sets in. So, while many worlds is a well-respected interpretation, the existence of tangible parallel worlds remains a claim. The evidence for it is merely that quantum mechanics works as it does, which is open to interpretation. No experiment has been devised that can say, yes, the other branch persisted. In summary, level 3 has a strong theoretical foundation, but whether it describes reality or is just a calculational tool is still up for debate. It's a case where the line between clue and claim is particularly blurry. The clues, quantum behavior, are real, but whether they imply an actual multiverse is a matter of interpretation. Level 4, the mathematical multiverse, is by far the most speculative of all. Here we step out of the realm of testable physics entirely and into philosophical territory. There are essentially no experimental clues that suggest all mathematical structures exist. Instead, what we have is an argument about the nature of reality and the unreasonable effectiveness of mathematics in describing the universe. It's almost a philosophical or metaphysical claim posing as a scientific hypothesis. Proponents might say that since mathematics underpins physical law so deeply, perhaps mathematics is the ultimate reality, and everything that can be math is out there. It's a bold extrapolation with zero direct evidence. It's hard to imagine any evidence for this idea. By definition, level 4 universes obey entirely different laws, and we could not interact with them. Unlike the multiverses of level 2 or 3 that emerge from equations we know, a level 4 universe could follow equations nothing like ours. So this concept remains outside empirical science. If there's any motivation for it, it's to answer why our laws are the way they are. Level 4 simply says no special reason, because every possibility is realized. But that isn't a testable answer, at least not yet. As of now, level 4 is a philosophical exercise showing how far the multiverse idea can stretch, but it stands without observational support. Now consider another multiverse notion: parallel universes in higher dimensions, the brain world scenario. Clues here come from theoretical physics that attempts to solve puzzles in our own universe's laws. For example, string theory suggests extra spatial dimensions and allows that our observable universe might be a 3D brain floating in a higher dimensional space. One hint is the relative weakness of gravity. Perhaps gravity's force is diluted by spreading into hidden dimensions. Scientists have attempted to detect evidence of this, measuring gravity at tiny scales for any deviation and checking particle collisions for energy missing into extra dimensions. So far, these experiments have not found anything definitively pointing to other dimensions or neighbor brain universes. That means up to now, the brain multiverse is purely theoretical, with no empirical confirmation. It's a bit like a complex answer looking for evidence. It elegantly addresses some questions. For example, what caused the Big Bang, or why gravity is weak. But until we actually detect extra dimensions, or some effect of another brain, say a cosmic pattern indicating a collision, it remains speculative. The brain concept does offer more tangible hope for tests than some other multiverse ideas. Extra dimensions might leave observable footprints, but so far, none have appeared. Here too, we have a claim grounded in advanced physics, still awaiting its clue. Related to brain worlds is the string theory landscape, essentially a multiverse of different possible physics. This one arises not from external observation, but from the internal logic of a theory. The clue, if we can call it that, is a surprise within string theory. Instead of one unique solution that yields our universe, string theory appears to have a colossal number of solutions, corresponding to different possible universes. The very existence of such a landscape in theory hints that maybe nature realizes many of these possibilities. It's a bit like a map with many cities. We know at least one city, our universe, is real on that map, and one might wonder if other cities are real too. So far, we only know our own to exist. We have not observed any of those other possible sets of physical laws. The string landscape remains a compelling explanation for fine-tuning. For example, why the cosmological constant is so small, but not zero, might be because only in such a valley of the landscape can galaxies form and observers exist. Yet, it's an explanation by default, not by proof. Critics point out that because you can explain almost anything by saying there's a universe where it happened, the landscape can at times feel like a very convenient but unfalsifiable construct. Proponents are trying to derive predictions, perhaps statistical ones, to test the idea. So far, no clear pattern or test from the landscape has been verified. Therefore, the string landscape remains a hypothesis born from a theoretical clue, still awaiting real-world corroboration. It's a claim that arose from our equations, but reality hasn't yet shown that any other part of that vast solution space is realized. So what about direct searches for evidence? We looked for signs of bubble collisions in the cosmic microwave background, but so far they've come up empty or inconclusive. One might consider this lack of anomalies as a clue in itself. Perhaps a hint that if a multiverse exists, it hasn't visibly interacted with ours. In other words, other bubbles could be so distant or so rare that they left no obvious imprint on our sky. Meanwhile, the measure problem is a clue of a different sort, a clue about the limits of our theoretical understanding. It signals that even conceptually, we have unresolved issues with making multiverse ideas predictive. Some interpret that as a hint that multiverse theories are incomplete or need new ideas to become truly scientific. On the other hand, solving the measure problem in the future could greatly strengthen these theories by allowing clear predictions. In summary, the experimental and observational side currently offers few direct clues of other universes. We have mostly constraints an absence of evidence. No clear bubble collision, no exotic particles from other brains, no breakdown of quantum laws pointing to other branches. These constraints don't disprove multiverse theories, but they remind us that extraordinary claims demand extraordinary evidence, which has not yet appeared. When we weigh the clues versus the claims across the multiverse landscape, we see that certain ideas rest comfortably on established science, like the continuation of our universe beyond view, while others are bold extrapolations, hoping to solve deeper puzzles, like the landscape explaining fine-tuning, or many worlds simplifying quantum puzzles. At present, none of the more exotic multiverse levels have direct evidence, turning them from intriguing theory into accepted fact. For now, these remain hypotheses that sit on a spectrum from the plausible to the fanciful. Still, scientists take them seriously because they address fundamental puzzles about our universe. But that's not the end of the story. It's worth noting that cosmology has been here before. There was a time when the existence of galaxies beyond the Milky Way was just a hypothesis debated without proof, until better telescopes settled it. The multiverse might be a similar case on a far grander scale, currently speculative, possibly provable in the future with new ideas or instruments, or possibly not provable at all. For that reason, many researchers keep an open mind, aware that today's speculation could be tomorrow's discovery. So where does that leave us? For now, multiverse theories straddle the boundary between science and conjecture. They are driven by profound questions and by successes of current theories, yet they remain unconfirmed. We must acknowledge that much of what we've discussed is a collection of intriguing what-ifs. Still, exploring them has value. It stretches our understanding and reminds us how much we don't know. If one day evidence does tip in favor of a multiverse, we will face a paradigm shift, realizing that our universe is just one of many. If instead it turns out there is essentially just one universe, we will have gained deeper insight by testing these ideas. Either way, we've pushed the boundaries of knowledge by entertaining these possibilities. Standing at this juncture of clues and claims, we find a healthy scientific tension. On one side, the desire to follow logic and mathematics to the grandest conclusions. On the other, the discipline to demand proof. This is the heart of the scientific process. Be open to wondrous possibilities, but also remain grounded in what evidence can support. As we prepare to step forward in our exploration, we carry both perspectives with us. In the next part of our journey, we will reflect on what embracing or refuting these multiverse ideas means, for science, for philosophy, and for our own sense of significance. Whether or not we ultimately find that the multiverse is real, grappling with the question itself takes us to the very frontiers of knowledge, and that journey is its own reward. Now, we gaze into the faint afterglow that bathes the entire sky, an ancient light carrying secrets from the dawn of time. In every direction, beyond all galaxies, a gentle whisper of heat persists in the darkness of space. This is the cosmic microwave background, the remnant glow of the Big Bang itself, still faintly visible as a nearly uniform curtain of light. For over 13 billion years, these photons have travelled, streaming from the hot plasma of the early universe once it cooled enough to become transparent. We are essentially seeing a baby picture of our cosmos, imprinted on the sky, a delicate backdrop against which everything else is set. The universe has kindly left us a photograph of itself as a swaddled infant, and we are learning to decode it. This background glow is invisible to human eyes. It's in the microwave part of the spectrum, but it is everywhere, filling the universe like a soft, uniform bath of light. Today, it is extremely cold and faint, just 2.7 degrees above absolute zero, but it carries with it the memory of a time when it was searingly hot and bright. Back then, it was a brilliant, blinding glow flooding space. Over billions of years of expansion, it has cooled and dimmed, shifting into gentle microwaves. The photons we detect now have been journeying through space for almost the entire age of the universe, only to end their long voyage when they encounter a detector on Earth. They are messengers from a time before any star had formed. If our eyes were capable of seeing microwaves, the night sky would glow softly everywhere we looked. A nearly uniform glow at just under 3 degrees above absolute zero, this radiation is remarkably smooth. It surrounds us on all sides as a dim, cool halo, almost the same in every direction, a testament to the early universe's hot, dense state. Yet this smoothness is not absolute. Sensitive maps reveal faint freckles in the temperature, tiny variations only a few tens of millionths of a degree. These subtle blotches and speckles are cosmic birthmarks, the imprints of the very first density ripples, the seeds that gravity would later sculpt into galaxies and clusters. It took until 1992 for these tiny ripples to be clearly confirmed, when NASA's COBE satellite measured slight warm and cool spots in the CMB. The discovery was electrifying. At last, concrete evidence of the primordial seeds that would grow into galaxies. One scientist remarked that seeing the CMB anisotropies was like seeing the face of God, a poetic way to express the profound feeling of glimpsing the universe's infancy. Later missions like WMAP and Planck mapped these temperature patterns with higher resolution and precision, revealing an exquisite match to theoretical predictions. The mottled pattern in the CMB is essentially a blueprint of all cosmic structure to come, the whisper of quantum fluctuations from the very early universe, stretched and amplified by inflation into the faint patchwork of hot and cold we observe today. It was a triumphant moment, confirming that the early universe wasn't perfectly smooth after all. When this whisper from the Big Bang was first detected in the 1960s, it was as a faint, persistent hiss of microwave noise with no obvious source. Two astronomers, Arno Penzias and Robert Wilson, were puzzled by a persistent static in their radio antenna. They even cleaned out the instrument, shooing away some pigeons nesting inside, thinking droppings might cause the interference. But the noise remained. Little did they know, they had detected the very afterglow of the Big Bang. At first, they were simply perplexed by the noise. In the end, they found they had been eavesdropping on creation. When the realization set in, it was a moment of awe, evidence that the early universe was once hot and dense, just as the Big Bang theory predicted. This faint hum was the remnant heat from that primordial fireball, now cooled to a whisper. Its discovery earned Penzias and Wilson the Nobel Prize, and it transformed cosmology overnight. It's astonishing to realize that every direction we look, we are essentially peering at a wall of light from the infant universe. The cosmic microwave background is often described as a curtain or wall, the surface of last scattering, beyond which we cannot see with light. Before that point in time, roughly 380,000 years after the Big Bang, the universe was an opaque fog of charged particles and photons constantly colliding. Once atoms formed and the fog cleared, photons could stream freely. Those are the very photons we see today as the background glow. In effect, this radiant surface is the farthest we can observe using electromagnetic waves, a spherical shell surrounding us at a great distance. Peering at it is like looking at a cosmic horizon. In effect, the CMB is a foggy glass that blocks our view of anything earlier. It marks the edge of the observable universe in time. We cannot see further back with light, because earlier than that, the universe was opaque. The sphere of the last scattering surface is about 46 billion light-years away in every direction today, much farther than 13.8 billion light-years, because the universe has expanded. Beyond it, if other realms or bubble universes exist, their light hasn't had time to reach us, or was never able to get through. It's humbling. There may be an infinite expanse beyond this shell of light, but it is hidden behind a cosmic microwave curtain. What lies beyond that horizon remains tantalizingly out of reach, at least by the light we know. In this faint background light, cosmologists search for any hint that our universe might not be alone. Most of the delicate ripples in the microwave sky can be explained by the physics of the Big Bang and cosmic inflation, the rapid expansion that smoothed and stretched the early universe. But scientists also pay close attention to any irregularities in this pattern that defy expectations. If our bubble universe had ever brushed against another, or if something lurks beyond cosmic horizons, a subtle clue might remain imprinted in this ancient light. Thus, the cosmic microwave background becomes a canvas where even the smallest anomaly could be a message from beyond our known universe. It's as if we are scanning a near-uniform painting for tiny cracks or odd brushstrokes that might tell of influences outside the frame. But the cosmic curtain holds more than just temperature clues. Hidden within this primordial light is a subtle pattern of polarization, a faint alignment in the way the light waves vibrate. As the young universe's first atoms formed and light decoupled, photons scattered off electrons, imparting a tiny preferred direction to their electric fields. The result is a delicate polarization pattern imprinted across the sky. This pattern remained undetected for decades, but now it has become another vital cosmic signal. By mapping not just the brightness, but also the orientation of the ancient glow, scientists can uncover even more about the first moments of creation. It's almost as if the universe, in that fleeting moment when it became transparent, left a soft crosshatch signature on the departing light. Polarization is a property of light we encounter in daily life. For example, sunlight reflected off water or glass becomes polarized, and polarized sunglasses can block it to reduce glare. We might think of it as light waves vibrating in a preferred orientation, carrying a whisper of the conditions under which they last interacted with matter. In the context of the CMB, polarization describes the orientation of the light's electric field as it travels. When the young universe's photons last scattered off electrons, the scattering imparted a slight alignment to the light. If the incoming radiation around an electron isn't the same in all directions, say there's a tiny hot spot in one direction and a cold spot in the opposite direction, the scattered light becomes polarized. Thus, the CMB's polarization pattern carries information about the distribution of those early hot and cold spots and about any disturbances, like gravitational waves, that were present at that time. We can imagine the primordial light as a sea of waves, where those waves encountered just the right imbalances, a bit of order, a polarization was left in their orientation. A key motivation for measuring this polarization is the theory of inflation. Inflation posits that the universe expanded by an unimaginable factor in a fraction of a second at the very beginning. This theory is undeniably bold, stretching our understanding of physics, yet it has been quite successful in explaining many observed features of our universe, including the origin of the CMB's temperature ripples. One as yet unobserved prediction of inflation is that it would have produced a background of gravitational waves, tiny ripples in spacetime itself. These primordial gravitational waves are like the faint ringing of a cosmic bell struck at the moment of creation. They would leave an imprint on the CMB's polarization. Specifically, while the dominant polarization, the E-mode pattern, comes from density perturbations, gravitational waves from inflation would generate a twisting type of polarization. the elusive B modes. Finding those swirls would be like discovering fossils from the universe's first trillionth of a second. It would be a relic of the universe's first heartbeat, tangible evidence of inflation's grip, and a hint that our cosmos might be just one patch in an ever-inflating multiverse. Such B-mode swirls would be a direct telegram from the Big Bang's earliest quantum tremors. Not all polarization is the same. There are gentle radial or snowflake-like patterns called E-modes, which were indeed first spotted in the cosmic background and matched expectations from primordial sound waves traveling through the hot plasma. But there is another, even fainter pattern researchers hope to find, a swirling, corkscrew polarization known as the B-mode. If we imagine smoothing out the polarization patterns on the sky, E-modes look like flower petals or spokes radiating in orderly fashion, whereas B-modes look like little whirlpools or eddies with a twist. These swirl patterns would be the fingerprint of those primordial gravitational waves rippling through the fabric of the cosmos when it was less than a second old. Gravitational waves from inflation would have tugged the sea of photons in a twisting way, sourcing B-mode polarization. Detecting that would allow us to target the signal of inflation at very high sensitivity without being swamped by the larger E-mode patterns. It's an amazing fact. Density perturbations only create E-modes, so any B-mode we find at certain large scales is like hearing the distinct tone of gravitational waves humming in the background. If those swirls are detected clearly, it would confirm that in those first moments, space itself rang like a drum, and that faint ringing is still embedded in the polarization of the light we see today. It would be a momentous discovery, akin to unearthing a fossilized footprint of the universe as a newborn. Detecting B-mode polarization is extraordinarily difficult. The signal is expected to be extremely faint, orders of magnitude weaker than the already tiny temperature ripples. It's like trying to hear a whisper in the middle of a loud symphony. The dominant E-mode polarization itself is only on the order of a few microkelvins, and B-modes are a small fraction of that. Furthermore, nature isn't kind. Our own Milky Way galaxy emits polarized microwaves from dust and electrons, which can masquerade as primordial B-modes. Over the years, experiments have refined their techniques to meet this challenge, using arrays of superconducting detectors chilled to near absolute 0, and placing telescopes at high, dry sites like the Atacama Desert and the South Pole, where Earth's atmosphere is thin and dry, minimizing interference. In 2002, a South Pole experiment, DASI, made the first detection of CMB polarization, the simpler E-modes, confirming yet another piece of the Big Bang puzzle. But the elusive B-modes from inflation remained the holy grail. In 2014, excitement ran high when a telescope at the South Pole, the BICEP 2 experiment, reported hints of these elusive B-mode swirls. For a moment, it seemed we had caught an echo of the Big Bang's inflationary burst, a faint imprint from cosmic dawn. Scientists around the world felt a surge of exhilaration. The cosmic dawn appeared to be speaking, confirming our boldest theories. But caution prevailed. Further analysis, particularly a joint study with the Planck satellite data, revealed that much of the swirling pattern could be attributed to polarized emission from interstellar dust in our own galaxy, which had subtly mimicked the primordial signal. What we thought might be a direct glimpse of the inflationary gravitational waves turned out to be foreground noise. It was a humbling reminder of how delicate this search is. Still, the quest did not end there. Ever more sensitive instruments are scanning the skies from high mountain plateaus and balloon lofts, and new space missions are on the horizon. They all seek the genuine article, the subtle polarization swirls imprinted by primordial gravitational waves. The pursuit of primordial B modes continues with fervor. New telescopes and satellites are being designed to push sensitivity even further. They will map broader swaths of sky at multiple microwave frequencies, striving to distinguish the faint cosmological pattern from the polarized emission of our Milky Way's dust and magnetic fields. It may take years, even decades, but the hope is that one day a clear B-mode signal from inflation will emerge. If and when it does, it will be a landmark moment, a direct glimpse into the universe's first instance, and a strong confirmation that inflation really occurred. And since many versions of inflation naturally lead to a multiverse, with inflation going on in other regions, spawning other bubbles, such a discovery would not only validate our inflationary theory, but also lend indirect support to the multiverse concept. It would be as if the universe itself finally whispered to us, "Yes, I did inflate, and in doing so, perhaps I gave rise to worlds beyond." As we chase those faint swirls in the sky, we also turn our attention to another cosmic messenger, the large-scale structure of the universe itself. Our quest for hints of a multiverse isn't confined to the cosmic afterglow. We also look around at how matter is arranged on the grandest scales, reading the universe's structure like a giant map. Over billions of years, gravity has drawn matter into a vast cosmic web. Filaments of galaxies and gas, clusters at the nodes, and immense voids in between. From afar, galaxies trace patterns like delicate threads woven through space. This large-scale structure grew from the faint seeds we see in the microwave background, and it provides another test of our cosmological theories. Over the past few decades, astronomers have painstakingly mapped the positions of countless galaxies to chart this cosmic web. Early surveys in the 1980s revealed hints of immense structures. For example, the Great Wall, a vast sheet of galaxies hundreds of millions of light-years long. It was the first clue that on very large scales, matter wasn't evenly distributed. Since then, projects like the Sloan Digital Sky Survey have expanded our cosmic cartography dramatically. Three-dimensional maps now show filaments and clusters spanning billions of light-years. These visualizations are breathtaking. Some liken it to seeing the neurons of a giant brain or the threads of a cosmic spiderweb. If you could fly through the universe at these scales, you would see galaxies strung along filaments like glittering beads on invisible strings, converging in great clusters at intersection points. In between lie enormous voids, vast black gaps where few galaxies reside, like the holes in a sponge or foam. It's an almost organic pattern. Threads of galaxies extend across space, intersecting in superclusters, while tremendous voids yawn between them. This grand design emerged from slight density differences in the early universe, growing under gravity's pull over eons. Seen through modern surveys, the distribution of galaxies is far from random. On the largest scales, it looks almost organic, a tapestry of filaments and voids. Some compare it to a web, or even the web-like structure of a sponge. The galaxies are arranged along twisting, thread-like filaments, great cosmic highways, hundreds of millions of light-years long, where clusters of galaxies form the busy intersections. Between these filaments lie huge black cavities, voids where hardly any galaxies shine. This cosmic web was actually predicted by theories of how dark matter and cosmic inflation seed structure. Tiny initial fluctuations in density, once stretched large by inflation and later amplified by gravity, would form just such filaments and clusters. Observing it in detail has been a triumph of modern cosmology, confirming key aspects of our standard model. Supercomputer simulations, starting from the nearly uniform early universe, with slight ripples like those seen in the CMB, produce a network of filaments and voids that closely resembles what we observe. The same theory that explains the CMB's spots also reproduces the statistical distribution of galaxies remarkably well. This success gives us confidence that our basic picture of cosmic evolution is on track. It is against this well-understood backdrop that any peculiar deviations, like anomalously huge structures or strange alignments, stand out so starkly. When something doesn't fit the pattern, it beckons us to investigate deeper, much as an odd note in a song would draw a listener's ear. Our own cosmic neighborhood is part of this immense tapestry. The Milky Way, along with the Andromeda Galaxy and dozens of smaller galaxies, forms the local group. This local group sits on the outskirts of a collection of galaxy clusters called the Virgo supercluster. And recently, scientists realized that even the Virgo supercluster is just a lobe of an even larger complex, our home supercluster, which they named Laniakea, Hawaiian for immeasurable heaven. Laniakea spans some 500 million light-years and contains tens of thousands of galaxies, including the Great Attractor region, drawing many galaxies inward. Within Laniakea, galaxies flow along gravitational slopes toward a central concentration. Yet Laniakea itself is just one region in the cosmic web. It is a reminder that even our massive Milky Way is merely one node among millions in a far-flung lattice of matter. With each new survey, the scale of known cosmic structures has grown. It was once thought that superclusters a few hundred million light-years across would be the largest coherent structures. Beyond that, matter should even out. According to the cosmological principle, if you zoom out far enough, the universe should look homogeneous and isotropic, the same in all directions. For a long time, observations upheld this. No structure larger than about 1 billion light-years was known. But newer cosmic maps have unveiled arrangements almost too colossal to comprehend. Vast walls and clumps of galaxies have been discovered that challenge the notion of cosmic uniformity. It's as if explorers mapping a featureless ocean suddenly found chains of islands, then continents. One example is the Sloan Great Wall, discovered in 2003, a filament of galaxies about 1.5 billion light-years long. Even more striking, in 2013, astronomers identified a structure called the huge LQG, Large Quasar Group, which stretches around 4 billion light-years. And in recent years, the Hercules Corona Borealis Great Wall was found, spanning an estimated 10 billion light-years, an order of magnitude larger than anything we expected under simple cosmological rules. Discoveries like these test the limits of our theories. According to standard models, a structure spanning 10 billion light-years shouldn't have had time to form since the Big Bang if matter was initially nearly uniform. Astronomers have catalogued a number of these giants: the CFA Great Wall, the Sloan Great Wall, the huge LQG, the giant gamma-ray burst ring, and the Hercules Corona Borealis Great Wall, to name a few. Each stretches across billions of light-years. Their existence doesn't outright break our cosmological theory, but it strains it. The worry is whether such vast arrangements had enough time to assemble in 13.8 billion years. Gravity works relentlessly, but can it pull together structures 5 or 10 billion light-years long in the time available? If not, perhaps our initial assumptions, or the early conditions of the universe, need revision. Some theoretical cosmological models can accommodate structures this large by allowing certain density enhancements or extended inflation scenarios, while others cannot. At the very least, these giants are telling us that the universe's uniformity has limits on extremely large scales. Astronomers debate whether these mammoth structures truly violate cosmic uniformity or simply represent the tail of the statistical distribution, rare, but not impossible, configurations in a vast universe. It's similar to tossing a billion coins. Somewhere in that immense series, you might get an unusual run of many heads in a row. Likewise, given enough volume, the universe might naturally produce a few very large structures by chance. Still, the sheer scale of these entities, each like a continent in the cosmos, raises eyebrows. According to the cosmological principle, any structure larger than about 1 or 2 billion light-years should be exceedingly unlikely. The presence of a 10 billion light-year Great Wall definitely challenges that principle. To some cosmologists, it suggests we might be seeing the limits of the smoothness of the universe, or perhaps subtle features of the initial conditions set by inflation. To truly test our cosmic assumptions, we also revisit the cosmic background with fresh eyes, examining whether its patterns are purely random, or if something strange lingers there as well. For the most part, the observed large-scale structure agrees with the standard cosmological model. The same theory of inflation, plus cold dark matter, that explains the CMB's tiny anisotropies, also reproduces the cosmic web's overall statistical properties. Simulations seeded with the CMB's ripples create virtual universes that look uncannily like the real one. Filaments, clusters, voids in the right proportions. This concordance is a triumph of modern cosmology, but it makes any deviations, like the enormous Great Walls or mysterious patterns in the CMB, all the more intriguing. They are small wrinkles in an otherwise consistent tapestry. When something doesn't fit the well-tuned symphony of data, it draws our attention like a discordant note. Returning to the cosmic microwave background itself, scientists have found a few curious features that don't quite fit the pristine picture. These are often called anomalies, small irregularities on the cosmic canvas that defy easy explanation. They are like tiny smudges or odd alignments in an otherwise uniform painting, hard to notice, but potentially meaningful. One example is an unusually large cold spot, a patch of sky slightly cooler than expected, spanning a region much larger than typical fluctuations. Another puzzle is a gentle imbalance in power between two halves of the sky. One hemisphere of the CMB shows ever so slightly stronger variations than the opposite hemisphere, as though the universe has a faint, two-faced asymmetry. And then there is a mysterious alignment of certain large-scale patterns, jokingly nicknamed the axis of evil by cosmologists. Here, the broadest ripples in the CMB, the very low-frequency, large-angle patterns, seem to line up in a particular direction, roughly along the plane of our solar system, a strange and unexpected correlation. The cold spot, in particular, has drawn much intrigue. It covers a patch in the constellation Eridanus and is cooler than the surrounding CMB by a few hundred microkelvins, millionths of a degree. More than one would anticipate for a random spot of that size. It spans roughly 5 to 10 degrees of sky, making it exceptionally large. To some, it's just an unusually cold blotch. To others, it could be a possible message from beyond standard cosmology. Some researchers have suggested that the cold spot might be caused by a gigantic supervoid, an enormous region relatively empty of galaxies, lying between us and the CMB. Photons passing through such a void would lose energy due to the integrated Sachs-Wolf effect, arriving cooler than they otherwise would. Indeed, surveys have found a region of lower galaxy density in that direction, sometimes called the Eridanus supervoid, on the order of 1 billion light-years across. But it's unclear if that void is large or empty enough to explain the entire cold spot dip. Other, more adventurous thinkers have posited that the cold spot could be the imprint of another universe beyond our own, essentially a bruise from a collision between our expanding bubble universe and another during the inflationary epoch. In that scenario, our bubble might have bumped against a neighbour, leaving a slightly cooler, more energetically disturbed patch in the fallout. This idea is highly speculative, and most evidence still points to either a void or a statistical fluke. But the fact that serious cosmologists even consider such an explanation shows how provocative this anomaly is. It's as if the cold spot is a quiet knock on the cosmic wall. Perhaps nothing, perhaps something very profound. The axis of evil alignment is equally perplexing. Normally, the CMB's hot and cold spots at large angular scales should have no preferred orientation. They should be randomly oriented across the sky. But analyses of WMAP and later Planck data indicated that some of the largest scale modes, like the quadrupole and octupole, which describe the pattern of temperature spots across the whole sky, are unexpectedly aligned with each other. Even more strangely, this common axis lies close to the ecliptic plane, the plane of Earth's orbit around the Sun. It's as though the universe has a special direction, which fundamentally rubs against the Copernican grain. We expect no orientation to be special. The chance of such an alignment happening randomly has been estimated to be low, a few percent or less, though there's debate on the exact number. Naturally, this raised suspicion. Could it be some subtle issue with the data? Perhaps unaccounted foreground signals or processing artifacts related to how we observe from within the solar system. Extensive tests haven't revealed any obvious culprit. It might still be a coincidence. After all, with enough data points one can find patterns by chance, or it might hint that our assumptions about perfect isotropy need revisiting. It's as if the universe has a faint, unknown tune playing in one direction, a notion that upsets the cherished idea that the cosmos has no preferred direction. Another odd observation is the hemispherical asymmetry. If you divide the sky into two halves, one half has slightly higher variance in temperature fluctuations than the other. It's a subtle effect, but it appears consistently in WMAP and Planck maps. It's as though the top of the universe's CMB is a touch different in character from the bottom. This again might be a statistical fluke. After all, we have only one sky to analyze, so any apparent asymmetry could just be random. But taken together with the axis alignment, it paints a picture of something a bit skewed in our universe's largest scales. These are like tiny irregular brushstrokes on an otherwise uniform canvas. What could these strange features mean? They tease us by hovering at the edge of statistical significance, whispering that maybe something is off in our simple story of a uniform universe. They might be nothing more than statistical flukes, random quirks that look significant but truly aren't, produced by our one and only universe just by chance. After all, with a whole sky full of data, some patch or pattern will always appear unusual, simply due to random variation. Indeed, many scientists remain cautiously skeptical, suspecting that these anomalies do not require exotic explanations. The conservative bet is that as we collect more data or understand our measurements better, these oddities will either fade in significance or find conventional explanations, like a supervoid for the cold spot. But others indulge in more adventurous speculation. Here is where science meets imagination in a responsible way, crafting hypotheses from curious data. Could the cold spot indeed be the imprint of another universe beyond our own? Could the axis of evil hint at some pre-inflationary pattern or anisotropy? Perhaps our patch of space inherited a slight twist or directional preference before inflation set in. These ideas are speculative, yet they show how even tiny blemishes in the cosmic backdrop can spark big questions. When confronted with such anomalies, scientists allow themselves to think outside the box, knowing full well that extraordinary claims require extraordinary evidence. It's a delicate balance, staying skeptical but curious, The anomalies are telling us, pay attention, something might be interesting here. And until we know for sure, they remain an open case file in cosmology. When the Planck satellite released its high-precision all-sky maps of the CMB in 2013 and 2015, it scrutinized these anomalies with a much finer comb. Planck confirmed that features like the cold spot, the hemispherical asymmetry, and the general alignments were indeed present in the data. They weren't obvious artifacts of measurement or data processing. This gave the anomalies a bit more weight. They're real features of our CMB sky. However, Planck also showed that the statistical significance of each anomaly is not very high. In plain terms, any one of these might still be a fluke, unusual but not impossible. Collectively, they are intriguing but not conclusive. The consensus in the community is cautious. These oddities could hint at something new, or they could simply be the kind of improbable patterns that occasionally emerge by chance. Because we have effectively only one universe to observe, one roll of the cosmic dice, distinguishing a true physical effect from a statistical accident is challenging. The signals are not screaming deviations. They're more like little murmurs that could either be meaningful or just random noise. Still, the fact that these puzzles persist through multiple generations of satellites keeps the door open. It encourages further analysis, more data. For instance, future missions to map the CMB polarization might shed light on these anomalies, and certainly fuels theoretical papers exploring if and how such features could arise from new physics. All the while, the cosmic background's little surprises are only one side of the coin. Anomalies in the sky's pattern are one thing. Anomalies in the motion of matter are another. Such hints of the unexpected aren't confined to the light we observe. They might also emerge from how galaxies and clusters move. And so, we turn to another curious tale. The possibility of large-scale flows hinting at influences beyond our visible universe. Not all cosmic mysteries appear as light in the sky. Some emerge from the motion of matter itself. We know, for instance, that our Milky Way galaxy and our local group is cruising through space at about 600 kilometers per second relative to the CMB. This motion shows up as a dipole anisotropy in the microwave background. It's slightly warmer in the direction we're moving and slightly cooler in the opposite direction, much like feeling a breeze more strongly in your face when you run forward. That particular anisotropy is well understood. It's caused by our galaxy falling toward a region of greater mass concentration, often called the great attractor in our local universe. We've identified nearby clusters and superclusters that exert gravitational influence, drawing us in. This known motion is attributable to gravitational attractions on relatively local scales. Our local group and the Virgo cluster, along with many other groups, are being pulled toward the great attractor, a dense region about 200 million light-years away in the direction of the Centaurus cluster. Beyond that, even larger structures like the Shapley supercluster, several hundred million light-years farther, contribute to a coordinated flow. These motions are part of the cosmic web's dynamics and are accounted for by the distribution of galaxies we observe. In short, our entire neighborhood is drifting in the cosmic currents set up by mass irregularities, and that's expected. What made the dark flow claim extraordinary is that it suggested a motion on a far grander scale, a coherent flow involving galaxy clusters at distances of billions of light-years, all heading in more or less the same direction, as if pulled by something well outside our visible universe. It was as if a faint current in the cosmic ocean was carrying matter that way, beyond the usual gravitational landscape we map. Think of leaves drifting on an unseen stream. If we noticed distant galaxy clusters all drifting in one direction, it would hint at forces outside our immediate view. Scientists who reported this phenomenon referred to it, evocatively, as dark flow, analogous to dark matter or dark energy. dark meaning unseen cause. They first reported this puzzling flow in 2008. A team led by astronomer Alexander Kashlinsky analyzed data from the WMAP satellite, combined with catalogues of galaxy clusters. They used a method involving the kinematic Sunyaev-Zeldovich effect, which can detect the motion of clusters with respect to the CMB by how the hot gas in clusters slightly perturbs the background light. After studying hundreds of clusters, they found a small but seemingly consistent velocity component, roughly 600 to 1,000 kilometers per second, toward a particular patch of sky, a 20-degree wide area roughly centered on the constellations Centaurus and Hydra. This motion appeared to be in addition to the expected random motions and the known flows towards structures like the Great Attractor. It was as if these far-flung clusters, spanning out to at least billions of light-years, shared a common destination beyond the edge of what we could see. The notion was stunning. Such a large-scale, coherent flow wasn't predicted by standard cosmology. To visualize it, imagine looking at thousands of distant galaxies and seeing that, after accounting for the normal motions, there's a subtle drift of everything toward one direction. This dark flow would be like a gentle breeze blowing across the entire observable universe, a breeze originating from something outside our cosmic patch. One proposed explanation for dark flow was indeed daring. Perhaps the gravitational pull of an extremely massive concentration of matter outside our observable universe, maybe a part of the multiverse structure or a previously inflated region, is tugging on our region. Some even speculated it could be a sign of another bubble universe's mass-leaking gravitational influence into ours. Though in general relativity, gravity is not supposed to propagate from outside our observable horizon in this way, so it's a very non-standard idea. Such suggestions were considered because no known structure within the observable universe could account for a coherent flow on that scale. This claim of a trans-horizon tug was met with excitement, but also healthy skepticism. It's a dramatic scenario. A sibling universe, or an unseen megastructure pulling our galaxy clusters, which, if true, would be an astounding clue of a broader multiverse, or something fundamentally missing in our cosmological model. Yet extraordinary claims require extraordinary evidence, and many in the community held judgment in reserve. Later studies, including detailed observations by the Planck satellite in 2013, cast serious doubt on the dark flow idea. Planck's improved measurements of the CMB and careful analyses found no convincing evidence of any such bulk motion beyond what standard cosmology predicts. In Planck's data, the motions of clusters appeared consistent with the normal expectations from known structures, without the need for an extra mysterious flow. It seemed that, as far as Planck could tell, the cosmos wasn't being obviously dragged by anything beyond the horizon. Some researchers noted that the statistical detection in the original dark flow papers was marginal and perhaps overstated. It's possible the earlier results were artifacts, subtle systematic errors, or noise quirks misinterpreted as a real signal. In summary, the universe, to our best measurements, isn't clearly exhibiting a dark flow. The clusters are not conclusively all drifting in one huge current that standard gravity can't explain. However, a few researchers continued to examine the data. In 2015, Kashlinsky and collaborators published an updated analysis using more clusters, including Planck data, and claimed they still saw signs of a consistent flow, albeit the results remained contentious. Tellingly, no further strong papers confirming dark flow have appeared since, and the topic has quieted. Most mainstream cosmologists remain unconvinced that dark flow is a real phenomenon. They suspect that the initial observation was a statistical fluke or an unnoticed systematic effect. Still, the notion remains intriguing. If a large-scale flow truly exists, even at a low level, it whispers of influences beyond our cosmic horizon. It's like a hint that our observable universe might feel a faint gravitational tug from something outside. It's a bit romantic. The idea that there's a pull coming from an unseen realm. As of now, though, the evidence for dark flow is not compelling. We have hints and claims, but nothing definitive, and indeed substantial evidence against it. For now, the dark flow belongs to the category of interesting ideas that await either confirmation or a fade into history as a footnote. There is also an ongoing careful check on the dipole anisotropy itself. That is, our solar system's motion relative to the CMB, measured by that dipole pattern of hotter and cooler sides. If our motion through the cosmos creates that dipole in the CMB, it should also cause a slight anisotropy in the distribution of distant galaxies. We should see a few % more galaxies in the direction we're moving because of relativistic aberration and density boosting, and slightly fewer behind us. Surveys of radio galaxies and quasars have been used to test this. By and large, the counts do show a dipole in the sky, consistent with our known motion. However, a few analyses have reported a discrepancy. The dipole in distant radio sources appears somewhat larger in magnitude than expected from the CMB dipole, and its direction, while roughly aligned, might not be exactly the same. It's as if the number of distant galaxies is anisotropic, in a way that doesn't perfectly match the simple prediction from our motion. If this difference persists with better data, it could suggest there's more to our cosmic motion than we thought. Perhaps an unseen large-scale density gradient, or even a hint that part of the dipole might not be purely kinematic. As of now, this dipole discrepancy is an open question, still within the margin of error of observations. Upcoming all-sky surveys with greater coverage and uniformity will clarify whether the distribution of distant galaxies truly mirrors our CMB dipole perfectly, or reveals a new puzzle. It's a subtle check, a murmur in the data, and scientists are paying attention to ensure our picture remains self-consistent. As surveys become more comprehensive, astronomers will be able to verify with greater certainty whether the distribution of distant objects truly mirrors our motion or hides any surprises. So far, we have explored patterns in the sky and motions of galaxies for clues of a multiverse. But what about the very constants that govern physics? If our universe is just one pocket in a grand multiverse, perhaps the fundamental constants of nature could vary from place to place or time to time. Imagine a universe next door where the strength of electromagnetism or the masses of elementary particles are slightly different. We cannot travel to such a universe, but we can check whether our own cosmos shows even a hint of spatial or temporal variation in these constants. If the fabric of reality had subtle differences across vast distances or over billions of years, it might be a sign that our universe is part of a larger mosaic of universes, each with its own settings. One way to test this is by studying light from the far reaches of the universe and seeing if the fingerprints of atoms, the spectral lines, have shifted in ways we don't expect. The idea is that if a constant, like the fine structure constant, alpha, which characterizes the strength of electromagnetic interactions, were different in distant regions or in the ancient past, the atomic spectral lines from quasars and galaxies, billions of light years away, would be at slightly different wavelengths than the same lines measured in laboratories on Earth. Astronomers have looked at the light from very distant quasars, which passes through intervening gas clouds, imprinting absorption lines like barcodes for elements. By comparing these to precise lab spectra, they can test if the atomic physics has changed over time or distance. Over the years, a few tantalizing studies have suggested there could be a spatial gradient in the fine structure constant across the sky, slightly higher in one direction of the universe and slightly lower in the opposite direction. In 2010, one research group, analyzing data from telescopes in both the northern and southern hemispheres, reported evidence that alpha might vary at the level of a few parts per million. It seemed larger in one hemisphere of the sky than the other. They described it as a dipole variation of alpha across the observable universe. If true, this would be a stunning result. It would mean one of nature's key numbers is not fixed everywhere, hinting that our local patch of universe might be one zone in a larger multiverse where alpha takes a certain value, while other zones might have different values. It would be like discovering that the laws of physics have a subtle seasoning that changes from region to region. However, such extraordinary hints remain unconfirmed and controversial. Other researchers, using independent data sets or different analysis methods, did not see the same variation. The supposed dipole in alpha might be due to systematic errors, slight differences in how data from different telescopes were handled, for instance. To date, no consensus has been reached that any fundamental constant actually varies in space or time. Most observations suggest that fundamental constants have stayed remarkably constant over the 13+ billion years of cosmic history, to the precision we can measure. Laboratory experiments with atomic clocks on Earth have likewise put extremely stringent limits on any changes in constants over time. If alpha or other constants are drifting at all as the universe ages, it's by less than a tiny fraction of a percent over billions of years. In fact, modern atomic clocks are so precise that they can test variation of alpha on the order of 1 × 10 to the -17 per year, and so far they have found no changes. Nature, it seems, is keeping her numbers consistent, at least within our cosmic region. This constancy is perhaps reassuring. It means the basic rules of physics are reliably uniform in our observable universe. It also underscores how special a discovery it would be to find any exception. The reason this line of inquiry is so compelling is tied to the so-called fine-tuning of our universe. Many fundamental constants appear to have just the right values to allow stars to shine, planets to form, and life, as we know it, to exist. It's as if the dials of physics were set precisely so that stable atoms can form and chemistry can unfold. If the strength of electromagnetism or the masses of particles were slightly different, stars might not produce heavy elements, or they might burn too quickly, or atoms might not hold together properly. This remarkable coincidence of constants is sometimes explained by the anthropic principle. In a vast multiverse of all possible constant values, we naturally find ourselves in one of the rare realms where the constants happen to permit complex structures and life, because only those regions can harbour observers asking the question. In other words, the universe's parameters might be random from one domain to another, but only those domains with a hospitable setting would ever be observed. This idea is both appealing and controversial. Appealing because it provides a reason for the seemingly fine-tuned nature of our constants without invoking supernatural design. But controversial because it's hard to test and can feel like a tautology. We observe this universe because it allows us to be here. The anthropic reasoning gains more weight if we have evidence that constants can indeed vary in different parts of a larger ensemble. If one day we clearly observed that alpha or other constants differ across the sky, even slightly, it would electrify the physics community. It would suggest that our universe's laws might be just one draw from a cosmic lottery, that beyond our horizon, the dials could be set differently. In essence, it would open a small window into the existence of other pockets of reality with alternate physics. However, to date, the hints of varying constants have not stood up to scrutiny. We must say that, as far as we can tell, the fine structure constant, the proton-to-electron mass ratio, and other such numbers are the same everywhere we look, to exquisite precision. Laboratory and astrophysical tests both support this uniformity. This lack of evidence for variation doesn't rule out the multiverse. The multiverse might still exist, but just produce domains where alpha by coincidence ended up nearly the same in our neighborhood. Yet it means we haven't gotten any direct experimental nudge towards different physics elsewhere yet. Nonetheless, the effort itself is worthwhile and telling. We have reached a point where humanity can check the stability of nature's laws across billions of years and billions of light years. That in itself is astonishing. It shows our capacity to probe deep questions about reality. And if one day a clear variation were detected, even a tiny one, it would send shockwaves through science. It would hint that what we consider constant and given here might not be so elsewhere. It would be a hint that our universe is part of a broader, varied multiverse. For now, nature's constants appear truly constant in our patch of spacetime, and the anthropic explanation for fine-tuning remains a philosophical point rather than an empirically confirmed aspect of physics. Faced with questions as vast and speculative as the multiverse, scientists often turn to the realm of simulations and mathematics. If we cannot directly visit other universes, perhaps we can create them, at least in a virtual sense, using equations or computers, and see what might happen. In laboratories of the mind, and in actual supercomputer simulations, researchers attempt to model how a multiverse might behave and what observable consequences it could have. They simulate bubble universes nucleating, growing, and occasionally colliding. They explore how different physical constants or initial conditions might influence the evolution of a cosmos. It sounds a bit like science fiction, building pocket universes inside a computer, but it's a serious way to explore theoretical possibilities where direct experimentation is impossible. By constructing toy models of eternity, scientists can glean insights into our own reality. One scenario often modeled is eternal inflation. The idea that inflation, once started, doesn't end everywhere at once, and in fact, may still be going on in distant regions. In this picture, our universe is one bubble that inflated and then stopped, leading to a big bang inside it. But elsewhere, other bubbles are still inflating or will inflate. Physicists set up simulations of a scalar field, the field driving inflation, with multiple vacuum states. In such simulations, a tiny region of false vacuum, a high-energy state, can randomly decay into a true vacuum bubble, analogous to a water droplet condensing in a cloud. They watch how that bubble expands at near the speed of light, and what happens when it encounters another bubble doing the same. These simulations are challenging because the scales involved are enormous, and the phenomena mix quantum effects with general relativity. Often, simplified lower-dimensional models are used, like simulating a 1 plus 1 dimensional universe, one dimension of space, one of time, which is easier to handle computationally. Even though they are simplifications, such models can capture pieces of the picture. In a computer's memory, tiny pretend universes flicker into being and either expand majestically or wink back out, depending on the rules set by the programmers. When bubbles form in a simulation, researchers can observe how their walls collide, merge, or produce shockwaves, and then extrapolate what that would mean for inhabitants inside those bubbles, like us. For example, a collision in a simulation might leave a distinctive round disturbance. Armed with that theoretical template, scientists could go look in the CMB for a similar round feature. In fact, Teams have done exactly this. They created algorithms to search CMB data for circular patterns, possible bubble collision scars. A few tentative hints popped up in earlier analyses. Even the cold spot was considered as one candidate. But so far, nothing stands out with high confidence as, yes, that was a bubble collision. Still, this shows how simulations help guide the search. Beyond pure digital simulations, some researchers have sought analogues of cosmic processes that can be tested experimentally. In one creative approach, a group led by physicist John Preskill used a kind of quantum simulation. They set up a line of many quantum bits, spins, which can exist in different states, mimicking a one-dimensional space. They managed to coax behavior akin to a bubble of one phase nucleating and expanding into another phase. This was essentially a very simplified, controlled analog of a vacuum bubble decay. It's a bit like making a tabletop model of a cosmic event to examine how it might work. Similarly, others have considered whether certain condensed matter systems, like superfluid helium or other phase transitions in the lab, could simulate aspects of inflation or bubble collisions. These analog experiments are in early stages and are, of course, very far removed from the actual complexity of a universe. But they have the same spirit as simulation: to probe the idea of the multiverse through indirect, human-made systems. By modeling scenarios of eternity, scientists can ask what-if questions on a grand scale. What if physical constants were different? What if two universes collided long ago? How often would bubble collisions occur in an eternally inflating space? And what detectable marks might they leave behind? Simulations allow such questions to be explored in a controlled way, at least in simplified form. They serve as a kind of theoretical laboratory. Of course, a simulation is only as good as its inputs and assumptions. The real multiverse, if it exists, could be far more complex than any model we run. Even our best supercomputers can only handle a tiny fragment of what a full cosmic landscape might be, often with reduced dimensions or idealized physics. Yet each step forward in simulation builds our intuition. By tweaking initial conditions and observing outcomes, researchers assemble a library of possible universes inside computers and their signatures. These become comparative models. If a particular simulated scenario produces a distinctive pattern, say concentric rings or a specific polarization signal, then observers can check our actual sky for something similar. In this way, theory and observation collaborate. Simulations generate hypotheses, and observations attempt to find them. The exercises act as a testing ground for our ideas, helping us refine which subtle clues to seek in the real cosmos, and which ideas might be too fantastical or inconsistent. There are, of course, limits to how well we can simulate an entire cosmos. Even with huge computational resources, we simplify and average out a lot of details. Yet the effort to simulate even fragments of the multiverse concept is valuable. It helps bridge the gap between the abstract mathematics of these theories and concrete predictions that observers can look for. We might never capture the full glory of an infinite ensemble on a computer, but even a glimpse, like an architect building a scale model, can tell us something about the structure of the whole. Even with imaginative simulations, we run into a fundamental conceptual puzzle when dealing with an infinite multiverse: the problem of probability. In an infinite collection of universes, how do we make sense of what's typical or likely? In our everyday experience, probabilities help us quantify chances, like the roll of dice or the likelihood of rain. But when literally everything that can happen will happen somewhere in an infinite multiverse, in fact will happen infinitely many times, the concept of probability becomes tricky. Imagine flipping a coin an infinite number of times. You would get an infinite number of heads and an infinite number of tails. The simple question, which is more common, heads or tails, suddenly becomes ill-defined. Both outcomes occur endlessly. Our usual logic for ratios doesn't straightforwardly apply when the numbers are infinite. This is not just a mathematical quibble. It strikes at how we'd extract predictions from a multiverse theory. If every possible outcome happens in some universes, how do we say what outcome we should expect to see in our universe? In technical terms, this is known as the measure problem in cosmology. Essentially, how to define a probability measure, a weighting scheme, on an infinite set of universes so we can meaningfully compare their occurrences. Different methods of regularizing infinity, that is, imposing some cutoff or rule for counting, can lead to wildly different answers. It's a bit like trying different ways to order an infinite list. Depending on how you do it, your tallies can change. One famous analogy given by physicist Alan Guth involves cows. If there are an infinite number of universes in which two-headed cows are born, and also an infinite number in which one-headed cows are born, what fraction of cows have two heads? The answer is undefined until you specify how you're counting the cows in each universe and comparing infinities. Our normal intuition fails in the face of the infinite. The question, are two-headed cows rare, is easy if we have finite numbers, but with infinite sets, any ratio can become ambiguous. Similarly, if there are infinitely many universes where George Washington was the first US president, and infinitely many where he wasn't, what is the probability that in a given universe like ours he was? It depends entirely on how you define the measure. Various proposals have been made to tackle this measure problem. Some approaches involve imposing an arbitrary cutoff. For instance, consider only universes or regions of spacetime below a certain large size or before a certain time. Calculate ratios there, and then let the cutoff grow and see if the ratios converge to a finite value. Others use more clever techniques, like weighting by the exponential expansion factor or focusing on the entropy produced. Each method has its quirks, often avoiding one paradox only to introduce another. For example, one naive measure gave rise to what's known as the youngness paradox, which effectively said that most observers should find themselves in a very young universe because there's exponentially more volume being produced at later times of eternal inflation, so fresh, rapidly inflating regions dominate the count. According to that measure, it would be exceedingly more probable to be in a universe that is only, say, 1 million years past the end of inflation, rather than 13.8 billion years past, which is what we observe. This is clearly in conflict with reality. We exist in an older, mature universe, not a seething, hot newborn. The youngness paradox signaled that measure was flawed. Researchers then adjusted their approach to avoid giving overwhelming weight to those ever-inflating young regions. By not overcounting regions that inflate longer, they resolved the youngness paradox in newer measures. These ambiguities give rise to bizarre thought experiments. In an eternal multiverse, there could be infinitely many planets with civilizations like ours, and also infinitely many strange scenarios. A famous example is the Boltzmann brain scenario. In an infinite timeline, random fluctuations could occasionally assemble a single conscious brain, complete with false memories of a life and world, out of chaos, only for it to immediately dissolve again. Such freak observers, Boltzmann brains, would vastly outnumber normal observers like us in some naive infinite counting schemes, because even though they are incredibly improbable in any given environment, if time is infinite and space is infinite, they eventually far outstrip the finite lifetime and volume of organized civilizations. If one naively compares infinities, one might conclude that a randomly picked observer in the multiverse is far more likely to be a disembodied Boltzmann brain than an evolved being living on a planet. That is an absurd and unsettling conclusion, since we clearly don't find ourselves as floating brains in a void. At least we think we don't. Clearly, something is flawed in that line of reasoning. It demonstrates that not just any way of counting universes will do. We need a sensible measure that yields sensible outcomes. One that says, for instance, observers like us in an ordered galaxy are overwhelmingly more typical than solitary brains popping up in empty space. To avoid such paradoxes, cosmologists are actively devising and debating measures. They aim to define probability in the multiverse in a way that matches our experience. We find ourselves in an old, structured universe as opposed to a young or chaotic one, and that avoids internal contradictions. It's a deep and subtle problem, touching on philosophy of science as much as cosmology. It forces us to formalize what we mean by saying something is likely when we have potentially infinite outcomes. Dozens of measures have been proposed: proper time cutoffs, scale factor cutoffs, stationary measures, causal diamond measures, and so on, each with technical pros and cons. As an example, one approach called the scale factor cutoff measure tries to avoid the youngness paradox by not giving excessive weight to regions that inflate far longer than others. Another approach, the so-called census taker, or causal diamond measure, focuses on what a single hypothetical immortal observer would see, hence, avoiding having to count everywhere at once. These technical constructs are beyond our scope to delve into fully, but the key point is that how you count infinities matters tremendously. One issue that cropped up in some measures was indeed the youngness paradox mentioned above. In some early measures, because volume was growing exponentially due to eternal inflation, the measure favored universes that exited inflation later, since they had more volume overall. That made it exponentially more probable to be in a very young universe that just recently stopped inflating, which contradicts the fact that we observe a 13.8 billion-year-old universe that had inflation end eons ago. Physicists realized they had to adjust their measures to penalize inflation that goes on too long, or at least not reward it unfairly, thereby avoiding this youngness problem. Similarly, they needed to handle the Boltzmann brain issue. Some measures that were proposed ended up either with a youngness paradox or an oldness paradox, where Boltzmann brains dominate, implying most observers live in heat-death eras as disembodied brains. Researchers have gradually found measures that avoid both the youngness and Boltzmann brain problems. For instance, the so-called stationary measure, or holographic measure, have been argued to dodge these issues. Yet, often those come with other peculiar predictions, like predicting bizarre values for physical constants that we don't observe. Each measure is like a different lens through which the multiverse can be statistically viewed, and getting a clear picture has proven tricky. The measure problem remains a profound puzzle. Few physicists consider it solved. It's very much an active area of research for those working on multiverse theories. Various proposals are on the table. Some as simple as cut off the counting at a certain time and then take a limit. Others more abstract, like defining an entropy or probability flux. Each proposal can yield different predictions for what a typical universe should look like. The challenge is to find a measure that A. avoids obvious paradoxes, like the youngness or Boltzmann brain issues, and B. yields predictions that match our observed universe's properties, like the values of constants, the amount of structure, etc., if possible. While no consensus exists yet, this work is crucial because it is the key to making the multiverse idea predictive. It forces us to think carefully about what we mean by probability and typicality in a nearly boundless context. In grappling with it, scientists hope to transform the multiverse from a philosophical musing into a framework that can make concrete predictions we could test within our universe. Taming infinity is no simple task. It may be one of the hardest conceptual problems we've ever faced, but step by step, researchers are trying to impose logic on the endless possibilities, hoping to extract meaningful answers. With these conceptual puzzles in mind, we finally ask, if the multiverse idea is correct, what evidence should we actually look for? What would definitive evidence of other universes even look like, given that we can't just see them directly? In a sense, we've been cataloguing the subtle fingerprints one universe might leave upon another, looking for indirect signals. Let's gather those threads. A collision between our cosmic bubble and another might have left a circular bruise in the cosmic microwave background, perhaps a strange circular pattern, or an unusually cold spot amid the random noise. The gravity of a neighbouring universe might tug on galaxy clusters, causing a slight but coherent flow, a dark flow, in one direction across huge expanses. Variations in fundamental constants could reveal that our region is not alone in setting the laws of physics. Even the detection of primordial B-mode polarization from inflation would indirectly point to a multiverse by confirming a mechanism, eternal inflation, that naturally gives rise to countless bubble universes. These are the kinds of signatures scientists have imagined and actively sought. Subtle, indirect, yet potentially telling. If the multiverse exists, chances are we will never see another universe outright. They would be separated from us by horizons far beyond reach. But we might see a fingerprint of one. For instance, if our bubble universe long ago interacted with another, the aftermath could be encoded in the CMB as a specific pattern. Simulations of bubble collisions predict that they'd create circular or oval imprints, spots where the temperature is a bit higher or lower, perhaps with a unique profile, a kind of bruise-like ring. Cosmologists have conducted searches in the CMB data for such features. So far, no compelling, unambiguous bubble collision imprint has been identified, though a few candidates were debated, including the cold spot itself at times. In fact, teams have put statistical limits on how common such collisions could be and still remain undetected. If too many had happened, we'd likely see something obvious by now, so there can only have been a few at most, within our observable patch, if any. It may be that collisions are extremely rare, or that our bubble was lucky enough not to hit any others in the small observable region we have. Another example. If fundamental constants varied across the sky, even slightly, that would be a strong clue for other domains. So far, as discussed, we haven't seen that. But the search isn't over. Upcoming instruments like high-precision spectrographs or next-generation telescope arrays will continue to test this with better accuracy. One more indirect evidence route is through gravitational waves. We mentioned that inflation's gravitational waves would confirm inflation itself. But there's also the possibility of gravitational wave backgrounds from bubble collisions or other cosmic events. In principle, if two universes collided, they would send out a burst of gravitational waves. These would be extremely hard to detect after billions of years, but who knows? A characteristic spectrum or pattern in a gravitational wave background, to be measured perhaps by future space-based detectors, might one day hint, controversially, at such an event. All told, scientists have narrowed down how evidence of a multiverse might manifest to a few avenues, and they've been actively looking down those avenues. So far, we have hints and anomalies, but no definitive proof. The fingerprints we've examined, unusual CMB features, tentative flows, potential constant variations, remain subtle and not clearly attributable to other universes, rather than mundane explanations. They remain enigmatic smudges, not smoking guns. It may be that our experiments and observations need to reach another level of sensitivity or breadth to find these clues, or it may be that such effects are genuinely very faint or rare. Either way, we persist in refining our search. The challenge is formidable, and it raises a profound question. Even if a multiverse exists, can we ever truly perceive it from within our own cosmic bubble? Perhaps evidence of a multiverse will always be indirect, teased out only from subtle anomalies and careful statistical analyses. Perhaps we will infer the multiverse the way one infers the presence of wind, by observing swaying trees. We'll never see the wind itself, only its effects. Or perhaps future breakthroughs, new kinds of observatories, novel particles, or theoretical insights, will open a clearer window, however small, onto worlds beyond our own. This line of inquiry also brushes up against the boundaries of science and philosophy. If other universes exist beyond all possible observation, can the multiverse idea be truly addressed by science? Or does it slip into metaphysics? For some, the multiverse lies at the edge of science, perhaps even beyond it. A cornerstone of the scientific method is testability, the ability to confirm or refute an idea through experiment or observation. If multiple universes are forever unobservable, except through subtle secondary effects, some critics argue that the concept drifts into philosophy rather than physics. It's a profound issue. Have we ventured into questions that science cannot empirically answer? Are we, in talking about the multiverse, doing science, or merely extending our imaginations? Others contend that the multiverse can still be approached scientifically, albeit indirectly. They point out that we often accept things we can't directly see if their effects are observable. For instance, we cannot see dark matter particles directly, but we infer them from their gravitational influence on galaxies. That's considered valid science. Similarly, if a well-established theory like inflation predicts a multiverse, and that theory's other predictions, like the CMB spectrum or polarizations, are experimentally confirmed to high precision, then it lends credence to the multiverse aspect of the theory as well. It's like seeing smoke from a fire we cannot reach. We might reason the fire is real, because everything else matches what the presence of fire would entail. In this view, we might never see other universes directly, but we can accumulate a convergence of clues that point toward them. So the debate becomes, is the multiverse a legitimate scientific hypothesis, or an interesting philosophical consequence? This debate is valuable because it forces us to reflect on what science can and cannot tell us, and how we define knowledge. For now, the multiverse idea straddles a line. It is grounded in serious physics theories, like inflation and string theory, and addresses real puzzles, like fine-tuning of constants. But it also reaches beyond what we can confirm in a lab or telescope. Many scientists take a pragmatic approach, continue to develop the theory, and look for any possible observational consequences. If the theory keeps proving useful and predictive in other ways, that's a kind of validation, even if the other universes remain shadows. Others keep a healthy skepticism. Without direct evidence, one should not multiply universes needlessly, a twist on Occam's razor. This brings us to the limits of empirical science. We stand at the shoreline of our observable universe, trying to discern shapes in the thick mist beyond. Perhaps evidence of a multiverse will always be indirect, gleaned from subtle fingerprints and whispers. Or perhaps one day, with new physics or technologies, we'll find a clever trick to probe the beyond. We continue to push against the cosmic curtain, refining our measurements and models as we go. Even without definitive answers, the quest itself is illuminating. Every time we push our boundaries, we learn something new about the cosmos and about our own limits. The search forces us to confront the possibility that reality is far more expansive than what we can see. It suggests that our observable universe, enormous as it is, might be a tiny island in a vast archipelago of universes. We find ourselves on this little cosmic island, peering out over an endless sea of mystery. In striving to understand whether there are other islands out there, we are participating in a story much greater than we ever imagined. And so, the journey continues. Without a final conclusion in hand, we carry on with curiosity and wonder. The universe has not given up all its secrets. Perhaps it never will. But in asking these questions, in searching the cosmic microwave curtain, mapping the galaxies, scrutinizing anomalies, chasing whispers of gravitational waves, and pondering infinite probabilities, we expand our own horizons. We may or may not eventually find proof of a multiverse, but along the way, we are sure to discover more about the universe we call home. The very pursuit transforms our perspective, making the night sky just a bit more magical and the laws of nature a bit more profound. It reminds us that we are part of a vast and mysterious reality, possibly one small part of an even grander multiverse, and that the act of seeking knowledge is itself a step into the infinite. The documentary journey does not end here. We flow onward, guided by the faint light of distant truths, into whatever lies beyond the universe we know. Our universe began in an exceptionally ordered, low-entropy state, like a pristine cosmic egg at the dawn of time, only to be broken and scrambled for all eternity. This one-way progression from order to disorder defines time's arrow. In everyday life we see it clearly. Eggs don't unbreak, smoke disperses but never gathers back, and we remember the past, not the future. Physical laws themselves are symmetric in time, yet the second law of thermodynamics introduces an arrow. In any closed system, entropy, disorder, tends to increase. Informally, things fall apart and cannot be put back together without expending energy. The great puzzle is why the cosmos started in such a low entropy, highly ordered state, a condition necessary for time to flow forward as it does. Was it a random fluke, a special initial condition, or something deeper? Scientists have long pondered this conundrum, searching for natural explanations of time's arrow across one world or many. One proposal invokes cosmic inflation, a burst of ultra-fast expansion early in the Big Bang that smoothed out the universe and reset entropy low. Inflation can indeed produce a vast, uniform cosmos, hence low initial disorder. But it comes with a twist. Once inflation starts, it might never completely stop. Quantum fluctuations could make inflation go on eternally in different regions, spawning infinitudes of baby universes, an ever-growing multiverse where every bubble has its own Big Bang. This eternal inflation picture provides a context for time's arrow. Each baby universe emerges in a low entropy state thanks to inflation's reset. Yet it raises new questions. If inflation is eternal, are there universes with time flowing differently? And can we test a process that creates realms beyond our view? Some cosmologists consider inflation's multiverse a wonderful feature, while others see it as a bug, since it's tricky to make concrete predictions in a scenario where everything that can happen will happen somewhere. In recent years, imaginative alternatives have arisen. What if the Big Bang wasn't the absolute beginning, but a transition point, with time fanning out in two directions from it? In a simple model by physicist Julian Barber and colleagues, a swarm of particles under gravity naturally evolved into a state of maximum density and uniformity, analogous to an initial singularity, and then expanded outward in both time directions. Essentially, the calculation suggested one past and two futures. The universe's history forks at the Big Bang-like moment into two mirror universes, each moving away from that central, low-entropy state. In this scenario, time's arrow in one universe points opposite to the arrow in the other. From our perspective in our universe, the other universe's time would appear reversed, its entropy decreasing. But for anyone over there, our side would look backward. As one description puts it, as time moves forward in one universe, it moves backward in the other. Yet each side sees itself as moving forward, and the other as the one reversed. It's a mind-bending idea that treats the Big Bang like a Janus point, a two-faced moment from which two time streams emerge. In principle, neither side could visit the other. They are separate, with a shared origin, but opposite arrows of time. Still, it's fascinating to imagine that the multiverse might contain a mirror cosmos, where cups unbreak and eggs reassemble, and that from that universe's view, we would be the backward ones. Even if there isn't a second time-reversed universe, thinking on cosmic scales forces us to confront the arrow of time and its consequences. If our universe, or multiverse, keeps existing indefinitely, eventually all orderly processes will run down. Stars will burn out, matter will spread thin, and entropy will approach a maximum. In that far future emptiness, odd things could happen by chance. Given infinite time, even extremely unlikely events become inevitable. This leads to a deeply weird notion, the Boltzmann brain. Named after physicist Ludwig Boltzmann, who first mused about fluctuating order from chaos. A Boltzmann brain is a hypothetical, self-aware entity that pops out of the vacuum due to a random fluctuation. In an eternally long, quiet universe, particles might just happen to jostle into the configuration of a functioning brain with memories and consciousness, a disembodied observer blinking into existence in the void. It would live only an instant before entropy dissolved its structure, but for that brief moment, it might believe it had a full life's worth of experiences. As absurd as it sounds, if the universe lasts forever, the brain out of chaos scenario is statistically unavoidable. In fact, in an infinite timeline, fleeting Boltzmann brains would vastly outnumber ordinary living beings who arise through slow evolution, because it's far easier for randomness to assemble a single brain once in a while than to assemble and maintain an entire biosphere for billions of years. This leads to a paradox. If the future is infinite and dominated by Boltzmann brains, then by pure probability, we ought to be Boltzmann brains with fake memories, since those would be more common than real, evolved brains at late times. Yet we clearly don't feel like disembodied momentary fluctuations. We see a coherent world and have records of a long past. That implies something interesting. Either our universe will not last long enough for Boltzmann brains to dominate, or our understanding of physics in such extreme conditions is flawed. Cosmologists take the Boltzmann brain problem as a serious cautionary tale. It suggests that an ever-expanding universe cruising toward heat death might not be the final story. If it were, we end up in logical knots about the reliability of our own memories. One way out is to suppose that the universe, or multiverse, has a kind of cut-off or rebirth mechanism. For example, perhaps there is a small chance that the universe will undergo a vacuum transition, essentially resetting physics and starting anew, so that eternity is broken into segments and Boltzmann brains don't get infinite chances to appear. Or perhaps universes that go to heat death are a dead end, and the only ones that persist are those that find a way to rejuvenate. In any case, Boltzmann brains remind us that deep time can produce deeply strange outcomes. They are a warning that some seemingly harmless assumptions, like an eternal, unchanging future, can lead to absurd conclusions. Our observable universe so far shows no sign of such randomness overtaking reality, which is a good thing. It means either we're nowhere near that end state, or new physics intervenes before it ever becomes an issue. One bold idea for cosmic renewal centers on black holes. Normally, we think of black holes as one-way traps. Matter and information fall in, and nothing comes out, aside from subtle quantum Hawking radiation. But some theorists have imagined that a black hole might be more than an end. It might also be a beginning. In this view, the interior of a black hole could form a seed for a new expanding region of spacetime, essentially a baby universe. Our own Big Bang, according to one speculative scenario, might have been born from the collapse of a star in some other parent universe. Conversely, every time a black hole forms here, the matter collapsing inside might trigger a bounce or a bud that becomes a separate universe inaccessible to us. It's a wild concept. Each black hole is like a cosmic womb, spawning a new universe that inflates with its own space and time. To observers in the parent universe, nothing ever comes out of the black hole. It just shrinks and maybe evaporates eventually. But from the perspective of the baby universe, its Big Bang was fed by the mass that fell into that black hole. The cosmologist Lee Smolin developed this idea into a framework called cosmological natural selection, or the fecund universes theory. He proposed that when a black hole collapses to a very high density, it doesn't form a forever singularity. Instead, it bounces into a new expanding universe. The fundamental constants of nature might get slightly randomized in the process, akin to genetic mutation. Therefore, each universe can give rise to many offspring universes, as many as it has black holes, and each offspring has inherited traits physics with a few variations. This leads to a Darwinian picture of the multiverse. Universes that have physical laws conducive to producing lots of black holes will have more children. Over cosmic generations, their lineage comes to dominate the population of universes. In other words, there is an evolutionary drive favoring universes that replicate prolifically via black holes. Our own universe, according to Smolin, might have parameters tuned for maximal black hole production, and that just so happens to also yield complex chemistry and life as a byproduct. It's a compelling explanation for why our universe's constants lie in the life-friendly range, not due to chance or providence, but because those constants maximize black holes, and we live in a universe that won the reproductive game. This theory makes unusual predictions. For instance, Smolin argued that if a slight change in a constant would increase black hole count, that change should have already happened in our ancestor universes. So our constants should sit at a local optimum for black hole production. He even predicted an upper mass limit for neutron stars. Since too massive a neutron star would collapse into an extra black hole, a universe. Fine-tuned for black holes would prefer that, unless prevented by particle physics. For years, the predicted limit was about 2 times the Sun's mass for neutron stars, and observations did find neutron stars around the 2 solar mass mark, seemingly supporting the idea. However, later discoveries pushed the record a bit higher, raising debates about whether the prediction failed or the theory can adjust. In any case, Smolin's scenario is appealing in that it tries to make the multiverse testable. It's not just philosophical musing, but a hypothesis about our universe's specifics, like particle masses and forces, that could, in principle, be falsified by astrophysical observations. Not everyone is sold on the idea of universes reproducing through black holes. Detractors point out issues. For one, can information truly transfer from a parent universe to the baby? If fundamental constants change, where does that new information come from? According to modern physics, information that falls into a black hole isn't destroyed. It may be encoded in subtle correlations in the Hawking radiation. If that's true, then a baby universe might not be completely independent. Or worse, maybe baby universes can't actually form because quantum gravity prevents the formation of a new, causally separate region. Skeptics like physicist Leonard Susskind noted that Smolin's idea, while clever, lacked a concrete mechanism and might conflict with the principle that information is conserved, no cloning or destroying of information. If the constants of a baby universe differed, that suggests some information was lost or created anew when the black hole formed, a scenario many find suspicious. Furthermore, without any interaction between universes, this theory might be forever beyond empirical reach, except via the indirect statistical predictions Smolin attempted. It remains an intriguing yet unproven piece of the multiverse puzzle. Even if it doesn't pan out, it gives us a way to think about the landscape of universes in a semi-natural selection framework instead of pure chance or design. Whether or not black holes are actually gateways to new universes, they have already gifted physics with revolutionary insights. In trying to understand what happens at a black hole's boundary, scientists were led to the holographic principle. This principle emerged from the discovery that a black hole's entropy, essentially the amount of information needed to describe everything about it, is proportional to the area of its event horizon, not its volume. In the 1970s, Jacob Bekenstein and Stephen Hawking found that the surface area of the event horizon, in units of tiny Planck squares, measures a black hole's entropy. That was puzzling. Normally, entropy scales with volume. It's as if all the information about the 3D contents of the whole is somehow stored on the 2D surface. Gerard T. Hooft and Leonard Susskind took this clue and proposed a bold generalization. Everything physically knowable about a region of space can be encoded on a surface bounding that region. In short, our universe might be like a hologram, where the true, fundamental description lives on a boundary, and the interior is a kind of projected image of that data. To picture this, imagine a huge sphere out in space that encompasses you and everything you see. The holographic principle says that if you had a tiny enough writing tool, you could record all the information about the contents of that sphere onto its surface, and that record on the surface would be enough to reconstruct everything inside. It's as though the boundary is as rich as the volume. This defies our normal intuition. We think more space means more information. But in quantum gravity, squeezing too much info in one place creates a black hole, suggesting a fundamental limit. You can't cram more bits of information into a region than an equivalent amount encoded on its boundary area. Our world, therefore, might be boundary-bound in terms of information storage. We live in 3 dimensions, but in some sense reality could be 2-dimensional. The 3rd dimension, and indeed time, could be emergent from a more primary 2D description. It's a bit like a holographic image on a film. The film is 2D, but when light shines through it, we see a 3D image floating in space. Likewise, the true degrees of freedom might reside on cosmic surfaces, and what we experience as 3D space is a kind of optical illusion of physics. This idea was made concrete in 1997 with Juan Maldacana's discovery of the ADS/CFT correspondence. He showed that a certain theoretical universe with anti-de Sitter ADS space, a specific kind of curved space with a boundary, is exactly dual to a conformal field theory CFT on that boundary. In essence, there's a one-to-one mapping between things happening in the 5D bulk space, ADS, and things happening in a 4D quantum field theory on its 4D edge. Every particle or process in the bulk can be described by particles and interactions on the boundary. This was a stunning realization. It was like discovering that a video game's world and the code running on a chip were two manifestations of the same information, one in a higher dimensional graphical form, the other in lower dimensional binary form. The holographic principle thus gained mathematical credibility. It implies that, at least for certain kinds of universes, space with gravity can emerge from a lower dimensional system without gravity. Many physicists suspect something like this is true for our own universe, though applying it to our more complex, expanding universe is harder. There might be a distant 2D surface, perhaps the cosmological horizon, or some abstract boundary in the mathematical sense, where our 3D universe's information is encoded. If our universe is a hologram in this way, it offers a novel perspective on the multiverse. Potentially, different universes could be like different patches of a single holographic screen, or different ways to project the same underlying truth. Imagine a holographic plate, where shining lasers from various angles produces different images. One might get a galaxy, another an island, depending on how you illuminate it. Similarly, one underlying theory might have many solutions or angles of projection that lead to different effective worlds, not directly interacting, but all represented in one unifying framework. Some researchers have even speculated that our universe's horizon could contain the information of other universes that branched off from ours or are otherwise entangled with our fate. These ideas remain speculative, but they underscore a theme. The boundaries might be where the secrets lie. The multiverse's separation might not be absolute. If everything is ultimately connected on a deeper, holographic level, then all universes might be part of a single cosmic tapestry, just woven in separate sections. To truly dig down to these fundamentals, we need a quantum theory of gravity, a unified framework that can describe the fabric of spacetime, Einstein's realm, in quantum terms, the language of atoms and particles. Several candidate theories offer glimpses of how such unity might permit or even require a multiverse. We've already touched on string theory and loop quantum gravity in their specific contexts, landscapes and bounces. But let's examine the broader picture of these quantum gravity sketches: strings, loops, and beyond. String theory arose as an attempt to reconcile gravity with quantum mechanics by positing that the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy. Each mode of vibration corresponds to a particle. One frequency gives an electron, another a photon, etc. And gravity emerges naturally from one of those vibrational modes, a closed string that behaves like a graviton. String theory is mathematically rich and beautiful, but it doesn't lead to a unique prediction for our universe. Instead, it allows a vast number of possible universes. The theory permits extra spatial dimensions, usually 6 extra, for a total of 10 spacetime dimensions in classical string theory, or 11 in its M-theory extension. These extra dimensions can be compactified, curled up into tiny shapes called Calabi-Yau manifolds, in an enormous variety of ways. Each distinct shape, and other choices like fluxes through those dimensions, yields different values for physical constants and particle types. By the mid-2000s, physicists realized that string theory has something like 10 to the 500 different self-consistent solutions, vacua, maybe even more. This was dubbed the string landscape. Initially, having 10 to the power of 500 possible universes was disheartening. It seemed we lost the predictive power of the theory. But then attitudes shifted. Perhaps all those possibilities exist in a grand multiverse, and we find ourselves in the one that supports life. String theory, then, wouldn't point to the one true universe. it would point to a multiverse of landscapes, with anthropic selection picking out our cozy corner of it. This line of thought was boosted by the realization that eternal inflation could populate the string landscape. Different regions of the inflating spacetime could get stuck in different valleys of that landscape, ending up with different laws of physics. Thus, string theory provided the multitude of possibilities, and inflation provided the mechanism to realize them in separate bubbles. Our universe would just be one bubble with one specific string vacuum. Other bubbles could be wildly different, some with different numbers of dimensions. Maybe there are universes with effectively 4 large dimensions of space instead of 3. Different types of particles, even different forms of physics altogether. In some, atoms might not form. In others, gravity might be stronger or weaker, etc. Most of those possibilities are not hospitable to complexity, but a few are, and naturally we must live in one of the hospitable ones. This marriage of string theory and multiverse is elegant to some and deeply unsatisfying to others. It leans heavily on the anthropic principle, more on that soon. It also means that certain questions, like why the proton's mass is what it is, might not have a neat answer in fundamental theory, but only a statistical answer across a multiverse ensemble. Some physicists, like Qumran Vafa, are working on the Swampland program to trim down the set of possible string theory vacua, finding criteria that most of those 10 to the power of 500 options don't satisfy, hoping to show maybe only much fewer are truly possible. The debate continues. Is the string landscape the end of our search for a unique theory because reality itself isn't unique? Or is it a sign we're missing a further principle that picks one from the many? For our purposes, string theory undeniably opened our minds to a reality much larger than previously imagined, one in which countless universes are not only possible, but quite possibly real. Now contrast that with loop quantum gravity, LQG, another approach to quantum gravity that takes a very different path. LQG doesn't postulate new dimensions or strings. It starts by reformulating Einstein's general relativity in quantum terms. Space is treated as a network of finite loops or links, sort of like an extremely fine mesh or fabric. Instead of space being smooth and continuous, LQG suggests it is made of finite chunks, quanta of space, on the order of the Planck length, about 10 to the negative 35th meters. These chunks are often described as spin networks, mathematical graphs where each link carries a quantum unit of area and each node carries a quantum unit of volume. In loop quantum gravity, space itself is discrete. There is a smallest possible volume, just as in ordinary quantum theory, there's a smallest energy quantum for a bound state. Time likely is quantized too, or at least the geometry evolves in discrete hops. The result is a picture of space-time as an ever-updating mosaic of granular units. On large scales, this mosaic would look continuous, just as a digital screen looks smooth from far away, even though it's made of pixels. But under extreme conditions, like near the Big Bang or inside black holes, the granularity becomes important and prevents infinities from forming. LQG has achieved an exciting result in this regard. When you use its equations to follow the universe back to what would classically be the t equals 0, Big Bang singularity, you find something remarkable. The singularity disappears, replaced by a bounce. Gravity, which is normally attractive, turns repulsive at densities around the Planck scale. The universe's contraction halts and reverses into expansion. Thus, in loop quantum cosmology, the application of LQG to the whole universe, the Big Bang was actually a big bounce. Our universe could be the expansion phase following a previous contraction phase that had shrunk everything down to an ultra-dense state, but never to infinite density. Before that bounce, there might have been another universe, with its own stars and galaxies, collapsing. And before that, perhaps another expansion, and so on. It opens the door to a cyclical or oscillatory universe, potentially an infinite stack of eons, each one giving rise to the next. This is a very different kind of multiverse, temporal rather than spatial. We don't have many universes at once, but one universe succeeding another in time. Still, from a grand perspective, it's a multiverse of sorts, a chain of universes with no beginning or end, each connected through a bounce. Loop quantum gravity's predictions are still being explored. If the universe did bounce, there might be subtle imprints on the cosmic microwave background, or the large-scale structure of galaxies, though any such signature from before the bounce might be incredibly diluted by the violence of the rebound and cosmic inflation. If inflation happened after the bounce, it would wash out most pre-bounce information. Researchers are devising clever ways to potentially see traces of a pre-Big Bang state in coming observations, but it's challenging. Nonetheless, the bounce idea has enormous appeal because it offers a solution to the initial singularity problem and naturally accounts for a low entropy start. If a universe crunches down, its entropy might be confined and then effectively reset at the bounce. It also means the arrow of time we experience from the bounce forward might just be one branch of a larger, symmetric time evolution, somewhat akin to the two-sided time scenario we discussed earlier, but here realized through a collapse-expand cycle rather than two divergent expansions. If true, it means time extends forever in both directions, and the question, what happened before the Big Bang, would be answered. A previous universe happened. Our Big Bang would not be the ultimate beginning, just a transitional stage. Apart from strings and loops, there are other frameworks vying for the role of quantum gravity. Causal dynamical triangulations, CDT, for example, builds spacetime from tiny simplices, like 4D triangular building blocks, and tries to sum over all possible shapes of spacetime. Interestingly, it finds that a large-scale classical spacetime can emerge from microscopic chaos, with time behaving in a surprisingly regular way. Asymptotic safety is a program where gravity's quantum behavior becomes well-behaved, non-divergent, at high energies, thanks to a fixed point in the renormalization group flow. If proven, it might give predictions for high-energy physics without needing extra dimensions. Then there are hybrid ideas. String theory itself has branched out into new domains, like the holographic duality, as we saw, and connections with quantum information. Some proposals, like ER equals EPR, blur the line between geometry and entanglement, hinting that the two may be aspects of one reality. And there are the more speculative ones. Perhaps our universe is literally a simulation in an even higher level structure, a kind of computable multiverse. Or maybe new physics will reveal hidden variables that connect what now seems separate. While each approach has its differences, a common thread is emerging in modern thought. Spacetime might not be fundamental. It could be an emergent property of more basic constituents, much like temperature emerges from molecular motion, or a fluid's behavior emerges from trillions of atoms. In such a scenario, asking if there are many spacetimes, many universes, might be like asking if a computer can run many simulations. Yes, if you have the memory and processing power. The true substance of reality might be something like quantum information, algebraic states, or some pre-geometric brew from which familiar universes crystallize like ice forming in water. A striking illustration of this comes from combining quantum mechanics and gravity via information theory. Physicists have suggested for over a decade that spacetime and gravity may emerge from quantum entanglement. In certain toy models of holography, if you reduce the entanglement between parts of the system, the fabric of space begins to tear or separate. Literally, less entanglement means less connected space. Conversely, the dense network of entanglement in a quantum state can sew together a smooth spacetime. As one researcher, Mark van Ramsdonk, put it. If two regions of space are not entangled at all, they're effectively in different universes. If you then entangle them, a bridge of spacetime might form between them. This is evocative of ER equals EPR, the conjecture by Leonard Susskind and Juan Maldacena that an Einstein-Rosen bridge, ER, essentially a wormhole, is equivalent to an EPR pair, which is a pair of maximally entangled particles. In their slogan, ER equals EPR, they suggest that every tiny thread of entanglement is actually a tiny thread of connectivity in spacetime. Your left and right electrons being entangled could, in an extreme metaphor, be connected by a Planck-scale wormhole. Taking this seriously implies that what we perceive as the geometry of space, distances, curves, holes, might really just be a reflection of how information is knit together in the quantum state of the world. Space is the quantum knit of reality. If space-time is emergent from entanglement and more abstract degrees of freedom, the multiverse could be understood in a new light. Different universes might just be different states or sectors of one grand quantum system. Imagine a vast quantum state that encompasses all possibilities, what one might call the wave function of the multiverse. In certain regimes or factorizations of that state, you get what looks like a classical universe with its own space-time. In another regime, you get a different universe. They may be superposed or independent, depending on whether there's any entanglement or interaction between them. In the many worlds interpretation of quantum mechanics, a different context of multiverse concerning branching possibilities in one universe, all branches exist in a larger quantum state, but don't communicate. Similarly, emergent universes might all exist in a bigger structure, but be effectively separate, because the entanglement that would connect them is not present, or is very limited. However, they're all really part of one unifying reality. It's a bit metaphysical, but it suggests the boundaries between universes might be less rigid if you can find the right description. We don't yet have the equations to carry this out for the real world, but research in quantum gravity, like it from qubit approaches, is attempting to toy with such ideas. The takeaway is that space and time could be epiphenomena, like how a shimmering mirage appears real, but is a product of deeper conditions. If we master those conditions, we might in principle program universes, or understand how one cosmos could morph into another by rearranging fundamental entanglements. Those are dreams for now, but they illustrate how far our conception of reality has evolved from the simple one universe, static space, linear time picture. We are, in a sense, unmooring space and time from their throne as the absolute background, and realizing they too are part of the natural order that can vary, stretch, or even multiplicity. Amidst all this exotica, a practical question arises. Even if other universes exist, whether as separate bubbles, brains, quantum branches, or emergent layers, can they affect us in any way? Or conversely, could we ever reach out and touch them? This is a question of causality and elsewhere. What can touch what across the boundaries of reality? Thus far, we've mostly assumed other universes are completely disjoint. But let's examine possible exceptions or subtle connections. In standard cosmology, even within our single universe, there are limits to causal contact. We cannot see beyond the cosmic horizon, about 46 billion light-years away, because light from those regions hasn't had time to reach us. Those regions are essentially cut off. They might as well be another universe from our standpoint, since no signal we send now could ever catch up to them. Space is expanding too fast. In the distant future, more and more regions will slip beyond reach as expansion accelerates. So, even a single universe can have causally isolated domains. If space is infinite, there could be civilizations forever unreachable, their light perpetually one step behind the stretching space. We might regard each pocket beyond our horizon as its own mini-universe with the same laws of physics as ours. This isn't the multiverse usually meant in theory, but it demonstrates that causal separation is a key factor in defining a universe. If you and I can never exchange information, even in principle, we inhabit effectively separate worlds. When people talk about multiverse scenarios like bubble universes from eternal inflation, they often picture these bubbles as like soap bubbles in a vast foamy space, mostly not touching, but maybe occasionally colliding. If our bubble universe had collided with another in the past, there might be a telltale imprint. Cosmologists have actually looked for such imprints. For example, a collision might slightly disturb the uniform glow of the cosmic microwave background, perhaps leaving a circular bruise or a specific distortion. Researchers have developed methods to search for evidence of bubble universe collisions in the sky. Up to now, no clear evidence of a collision has been found. We haven't spotted an unmistakable circular ripple or temperature anomaly that screams cosmic fender bender. But the searches have placed interesting limits. If a collision had deposited too much energy into our universe, it could have either destroyed primordial structures or left big anisotropies, things we don't observe. So if collisions happened, they likely were glancing blows, or far from our observable patch. The absence of obvious collision marks is consistent with the idea that if other bubbles exist, they're either far away or separated by large inflationary expansions, so that we only see our bubble's homogeneous interior. Still, it's remarkable that this once purely speculative scenario has graduated to something we can at least attempt to check. The quest continues, using ever better data from satellites and telescopes to see if there's any subtle pattern, perhaps a polarization signal or a small temperature variation that could hint we encountered another universe long ago. It's a long shot, but as one cosmologist said, it's a search for evidence of something you thought you could never test. Even a null result, finding nothing, is useful. It tells us that if collisions happen, they must be either extremely rare or low impact in our cosmic neighborhood. Another possible contact point is through gravity. If other universes exist in extra dimensions, as in some brain world scenarios of string theory, it's conceivable that gravity, which can spread through dimensions, might feel the presence of neighboring branes. For example, there are speculative models where our universe is a three-dimensional membrane floating in a higher dimensional space. Other brane universes might be nearby in those extra dimensions. We wouldn't see them directly, our particles and light are stuck to our own brane, but gravity leaking between branes might cause subtle anomalous effects, like changes in how gravity behaves at certain scales. Experiments testing Newton's law at sub-millimeter distances, for instance, are partly motivated to check for such leakage, so far finding none beyond the expected. If one brane collided with another, some theorists suggested that could be an alternative explanation for the Big Bang itself, a brane collision releasing energy that becomes a hot universe. While these ideas are hard to verify, they at least offer channels through which universes might interact, via gravity or high-dimensional dynamics. Then there's the idea of wormholes, or bridges. In principle, general relativity allows for wormhole solutions, tunnels connecting two distant regions of spacetime. Sci-fi loves the idea of using wormholes to travel within a universe or even between universes. If a wormhole connects two universes, they're not really separate anymore. They become one connected system, like two mouths opening into a shared throat. Classical GR wormholes typically require negative energy, exotic matter, to hold them open, otherwise they pinch off. Quantum physics entertains the notion of quantum wormholes, or spacetime foam. At extremely small scales, perhaps tiny tunnels constantly form and evaporate. Could one of those tunnels ever enlarge or be stabilized? If yes, maybe an intrepid and extremely lucky traveler or message could slip through. Physicists like Susskind have joked that traversable wormholes might be the only way to truly test the multiverse. If you could go visit another universe, then it stops being metaphysics. As of now, traversable wormholes remain speculative and seem to violate some energy conditions. But intriguingly, recent research in quantum gravity, in the context of ADS/CFT, showed that under certain conditions, wormholes and entanglement are directly related, and that a message can be sent through a special kind of quantum-correlated black hole pair. It's very theoretical and not applicable to real-world universes yet, but it hints that the fabric of space-time might allow stranger connections than we thought, provided quantum mechanics is taken into account. How about quantum parallel worlds? The many worlds interpretation of quantum mechanics says that whenever a quantum event has multiple outcomes, all occur in separate branches of the wave function. Those branches quickly become effectively separate universes that do not interact. Decoherence cuts the communication. In principle, however, these branches exist in a shared Hilbert space. Could there be interference or interaction between them? Normally, decoherence is for all practical purposes irreversible. The branches won't rejoin to produce noticeable interference patterns once macroscopic differences have formed. However, if one had godlike control of all particles, one could, in theory, recombine branches, just as in a lab, one can recombine split waves in a double-slit experiment. For macroscopic universes, that's not feasible. Yet, theorist David Deutsch once speculated about quantum computers that could leverage other branches' computations, effectively communicating with alternative outcomes to speed up calculations. And physicist Anthony Valentini has argued that perhaps there is a loophole in quantum mechanics via non-equilibrium hidden variables that would permit what he calls signal non-locality, the ability to send messages using quantum phenomena that standard quantum theory forbids. If such a loophole existed, one might at least detect the existence of other quantum branches, if not send a meaningful message. So far, all experiments conform to ordinary quantum mechanics, so there's no evidence of crosstalk between parallel outcomes. Many worlds likely remains a multiverse that, while real in theory, is hermetically sealed between branches. Each version of reality can only watch its own story unfold, unaware of the countless siblings splitting off at every quantum decision. In summary, the consensus is that if a multiverse exists, direct interaction between universes is exceedingly unlikely. They either lie beyond each other's horizons, or in different dimensions, or in separate quantum branches, and none of those situations easily permits a handshake. That's why skeptics sometimes say, if we can never observe or affect these other universes, are they really part of science? It's a valid point. However, as we've seen, scientists are clever. They look for indirect evidence, a bruise in the cosmic microwave sky, an unexpected blip in gravitational laws, a missing probability mass in quantum experiments, etc. We haven't found anything conclusive, but the very act of looking pushes the boundaries of what we can test and understand. It might turn out that the universes truly cannot touch. In that case, we must rely on internal consistency of our theories as evidence, a more abstract, yet possibly the only, approach. If a theory that predicts a multiverse also accurately predicts many things we can measure, then we start believing in the parts of it we can't directly see, similar to how we believe in electrons, though we can't see them individually, because the theory that posits them works so well. In that spirit, Many physicists treat the multiverse as a plausible inference, not proven, but worth considering if it naturally falls out of well-tested physics. Others urge caution. They worry it could lead us to accept untestable ideas and stray from the empirical backbone of science. This tension is healthy. It keeps the field vibrant and grounded at the same time. We now come to an introspective part of our exploration, examining our own bias in observing the universe. Selection effects play a key role in any discussion of multiple universes. The most famous is the anthropic principle, which we touched on in relation to the string landscape. The anthropic principle, in essence, says, the reason we observe certain fundamental constants or conditions is that if they were otherwise, we wouldn't be here to observe them. In a multiverse with varied properties, only those patches that can harbour observers will have someone asking, why are things this way? It provides a kind of filter on our observations. Our universe's properties, such as the strengths of forces, particle masses, the dimensionality of space, the rate of expansion, might be just one random draw from a vast ensemble. Most draws don't allow complexity or life. A few do. We necessarily find ourselves in one of the lucky draws. So while the true underlying distribution might be huge and varied, our data are conditioned on the requirement that someone is around to collect the data. This anthropic reasoning has been used to explain why, for example, the cosmological constant, the energy of empty space causing accelerated expansion, is incredibly small, but not zero. If it were much larger, the universe would have expanded too fast for galaxies and stars to form. Much smaller, or negative, and the universe might recollapse or look very different. In the multiverse context, many universes will have zero or huge vacuum energy, sterile and empty, and we live in the rare one where it's just in the narrow, life-friendly range. In fact, physicist Steven Weinberg, in 1987, used anthropic arguments to predict a cosmological constant in that narrow window, years before dark energy was discovered. When it was observed in 1998 to be small but positive, some took it as a tentative win for the anthropic multiverse idea. However, the anthropic principle is contentious. Some scientists embrace it as a sensible explanation for why our bubble looks so special. They point out that it's essentially true by definition. We shouldn't be surprised to find ourselves in a universe that permits our existence, because we couldn't exist in the other kinds. It addresses the otherwise puzzling fine-tuning of the cosmos, the unlikely seeming coincidence that a number of fundamental parameters lie in the tiny range that allows atoms, stars, and life. But other physicists strongly dislike anthropic reasoning, because it can feel like giving up on deeper understanding. They argue that if we invoke "we're here, so it must be like this" too readily, we may be missing a hidden principle or mechanism that actually determines those constants. Moreover, anthropic arguments risk being non-falsifiable. How do you prove that we live in one of many universes versus there is only one universe that had to have these constants? If anything we observe can be back-justified by "otherwise we wouldn't be here," it becomes a tautology, not a predictive theory. To illustrate, consider a classic analogy. Suppose an astronaut is randomly dropped somewhere on Earth. He finds himself breathing air at a temperate latitude, on solid ground rather than in the ocean. Initially, these conditions might seem implausibly lucky. Most of Earth's surface is water or uninhabitable extremes. But the selection effect is clear. If he weren't in a survivable spot, he wouldn't be alive to realize it. Does that explain why Earth has those survivable spots? Not really. It just explains why he's currently experiencing one. The formation of Earth's habitable areas still required geophysical processes, The anthropic reasoning only explains the conditional probability of his location given that he's alive. In cosmology, it's similar. The anthropic principle alone doesn't build universes. It only selects among them from the viewpoint of an observer. So some feel it's at best half an explanation. Smolin famously called the anthropic principle not even wrong, urging that we seek scientific alternatives to the anthropic principle. His own cosmic selection theory was one such attempt, trying to predict something, like neutron star masses or certain particle values, that could be checked, rather than just asserting we got lucky. Other physicists, like Paul Steinhardt or Roger Penrose, have been vocal that invoking a multiverse and anthropics is premature, and that it might indicate we're on the wrong track with theories like string inflation if they require an anthropic crutch. Meanwhile, proponents like Susskind counter that if the universe is part of a multiverse, then refusing to accept anthropic explanations would be refusing reality. They often point out that historically, accepting that Earth was not the center of the solar system, or that our galaxy is not the only one, were humbling shifts, and the multiverse might be another step towards humility. In their view, the multiverse and anthropic principle do yield a kind of prediction that certain parameters, like the cosmological constant, will be within the narrow window for life, but otherwise seemingly random within that window. If we find some constant that sits right at the edge of that window, like dark energy is just enough to allow galaxies but not much more, it feels suggestive. If we found our universe is too finely tuned in ways that even multiverse distributions can't explain, that would be evidence for something else. It's a nuanced debate. What's clear is that anthropic reasoning is most useful when we have a prior understanding of the distribution of possibilities. For example, if string theory told us that vacuum energies are uniformly distributed across many decades, then having a tiny non-zero value in our universe could be statistically weighed. If it's 1 in a million for a universe to have such a small vacuum energy, then seeing it suggests either incredible chance or an observer selection, since only in that millionth universe does life form. If instead theory says vacuum energies tend to cluster near zero, then our value is not surprising, and no anthropic story is needed. So, anthropic arguments often go hand in hand with theoretical assumptions about the multiverse's population. In practice, it's hard to know that distribution without a firmer theory of the multiverse. It's like we have one ticket, our universe, and it's a winner, but we don't know how many tickets were in the lottery to start with. Was it 1 in a billion or 1 in 10? That makes a difference in how we view the result. Nevertheless, the anthropic principle has become part of the language in cosmology. It reminds us that observation is biased, not by malice or flaw, but by the simple fact that dead observers don't observe. We must take into account that any data we collect comes from a physical environment that permitted our existence. This principle is uncontroversial in limited domains. Astronomers know we live on a planet at a comfortable distance from a stable star. So obviously we shouldn't be surprised to find ourselves in such a Goldilocks spot. Extending it to the entire universe is more daring, but conceptually similar. If indeed there is a multiverse of all kinds of universes, we should not be amazed that we are in one of the rare universes that allow intelligent life. It could not be otherwise. So, in a curious way, the anthropic reasoning is a Copernican demotion and a special exaltation at the same time. It demotes us by saying we're not central. Many universes exist. We're just in a mediocre one that happens to allow us. But it also highlights how special our circumstances are relative to most of the multiverse. It suggests that much of the multiverse might be quite sterile or simple, and our rich, complex bubble is a rarity. This tension, being typical among observers, but atypical among all configurations, is something philosophers of science discuss at length. It also means any theory that involves an ensemble must grapple with selection bias in a quantitative way. That's a whole field called anthropic bias and self-selection theory. It's a bit like interpreting an experiment where you lost 90% of your data. You have to account for why that data is missing. In the cosmic experiment, 99.999% of universes might be devoid of life, and we'll never hear from them. We only hear from the tiny fraction that had someone to send a signal, or rather, to exist and ponder. That complicates inference, but not impossibly so. After wandering through these lofty ideas, time's arrow flipping in mirror worlds, freak brains blinking in and out, universes sprouting from black holes, reality as a hologram, space emerging from quantum threads, and selection bias on a cosmic scale, it's natural to feel a bit overwhelmed. Can we truly know any of this is true? Where does science end and speculation begin? This final section is about staying grounded, keeping our sense of wonder in check with healthy scientific skepticism and perspective. It's a reflection on how to navigate the thin line between imaginative theory and solid evidence. Firstly, it's important to acknowledge that much of what we discussed lies at the frontiers of knowledge, where definitive evidence is scant. That doesn't mean these ideas are pure fantasy. They often emerge from extending well-tested theories into regimes we haven't observed yet. But it does mean we must be careful not to confuse them with established facts. The multiverse, in whichever form, is at present a hypothesis, or a collection of hypotheses, not a proven reality. Some versions of it might be fundamentally unprovable, even in principle, and that has sparked debates about whether discussing them is scientifically meaningful. We should remember that historically, many beautiful and clever ideas turned out to be wrong when data eventually came in. The steadfast guide in science is experiment and observation. Without them, we risk building castles in the air. It's okay to build those castles. Theoretical exploration is crucial, but we must also be ready to let them crumble if nature doesn't cooperate. So how do we stay grounded? One way is by demanding internal consistency and some degree of testability. For instance, a multiverse theory might not allow us to visit other universes, but if it predicts certain statistical signatures in our universe, like we should find X type of particle, or dark energy should have roughly Y value, and those signatures are observed, then the theory gains credibility. Another way is by incremental confirmation. If more and more pieces of a framework get verified, say, inflation theory gains evidence through the pattern of cosmic fluctuations, and inflation implies a multiverse, then our confidence in the implied multiverse grows indirectly. We also cross-pollinate between independent ideas. It's intriguing that both string theory and inflation hint at a multiverse, and meanwhile the weird fine-tuning of our universe begs for an explanation. These lines of reasoning converge, which gives some folks enough confidence to consider the multiverse seriously, even before direct proof. It's a bit like how in the 19th century people believed atoms existed well before anyone saw one, because multiple lines of reasoning, chemistry, thermodynamics, all pointed that way. By the early 20th century, Brownian motion's explanation clinched it. Perhaps, analogously, one day, multiple indirect clues about the multiverse might add up to a compelling case. Another way to stay grounded is by recognizing what we don't know. It's okay to admit that we're speculating. For example, talk of other universes out there might be a useful analogy or model, but they could just as well be purely mathematical constructs with no independent reality. When we say universe, we're already at the limit of what we can conceivably observe, by definition. So anything beyond is extra tricky. We should then phrase conclusions carefully. Instead of, the multiverse is real, one might say, the multiverse is a possible outcome of our best, current theories under these assumptions. That's longer and less sexy, but it's the truth of the matter. We hope for a day when we can drop the caveats, but today is not that day. It's also worth noting that even within a single universe, physics has areas of vast uncertainty. Dark matter and dark energy, for instance, are unknown entities comprising approximately 95% of our cosmic makeup. It's humbling. We have this beautiful standard model of particle physics, and yet most of the cosmos is made of stuff outside that model. Similarly, our cosmological model works extremely well, yet it leaves key puzzles, like the entropy of the early universe, or the reason for exactly 3 large dimensions of space, etc. In confronting these, scientists understandably entertain radical ideas like multiverses, because conventional ideas haven't solved them yet. Wonder prompts us to open our minds to these possibilities. Restraint reminds us that extraordinary claims demand extraordinary evidence, as Carl Sagan famously said. At the moment, the evidence for a multiverse is either circumstantial or theoretical, so we should neither dismiss the concept outright nor swallow it uncritically. We keep it floating in the realm of the possible, investigating every angle by which it might be corroborated or refuted. There's also a philosophical ground. What is science's aim? If it's to explain what we observe, some argue the multiverse does that, by explaining fine-tuning and offering a larger context. If it's to predict new phenomena, the multiverse has limited ability to do so, since other universes are hard to access. Are we satisfied with an explanation that can't be verified beyond our one data point? Reasonable people disagree. Some take a pragmatic view. If a multiverse helps explain puzzling observations in our universe, like why physics has certain features, then it has done scientific work, even if we can't observe the other universes directly. Others take a stricter view. If those other universes can never be observed even indirectly, then their existence is not a scientific question, but a metaphysical one. And the explanation is not truly an explanation, just a reframing of ignorance. Both perspectives have merit. The field hasn't resolved this, which is why you'll find cosmologists both advocating for multiverse theories at conferences and others rolling their eyes at the same. From a human perspective, the multiverse idea also invites existential and even spiritual questions. If there are countless universes, what does that mean for the significance of ours, or of us? Some feel it makes us less special. We're one of zillions. Others find it awe-inspiring. Reality is even grander than we thought. Some worry it erodes purpose or design arguments. Others feel it elevates the miracle of consciousness, since even amid infinite universes, conscious life might be exceedingly rare. These reactions don't directly affect the science, but they remind us that whenever science pushes boundaries, as with heliocentrism or evolution in the past, it impacts how we see ourselves. Staying grounded in this sense means keeping an emotional and philosophical balance too. We let ourselves marvel at the possibility of infinities beyond infinities, but also cherish the particular universe we inhabit, the only one we directly know. After all, if the multiverse is real, then every universe is unique and precious in its own right, not just ours. And if it's not real, then our universe is the whole show, making it all the more significant to understand deeply. In practical terms, what's next? How do we continue exploring the multiverse idea responsibly? One approach is through more precise cosmological observations. Maybe subtle patterns of primordial gravitational waves or quantum noise could reveal hints of other domains or processes, like eternal inflation. Another is through particle physics. Perhaps we'll discover completely unexpected particles or phenomena that point to other dimensions or multiverse-like branching. Imagine, for instance, if we found a particle that occasionally disappears, possibly tunneling into a parallel brane. That would be huge. We also deepen our theoretical frameworks. maybe a true theory of quantum gravity, a successful theory of everything, will, by necessity, imply a multiverse, or, alternatively, rule it out by demanding only one self-consistent reality. Until then, we gather confidence in bits and pieces. If inflation gets a stronger empirical foundation, e.g., through primordial gravitational waves, the case for at least a vast universe, maybe even a level Y multiverse of regions beyond our horizon, gets stronger. If we find evidence of extra dimensions or supersymmetry at colliders, then some stringy ideas about multiple vacua gain credence. As this part of our documentary draws to a close, we refrain from final conclusions. The story of the multiverse is still being written, in equations, in telescopes, in thought experiments late at night. We've journeyed through many speculative realms, but now we return, in a sense, to our starting point. The world we see, the data we have, the mysteries we have yet to solve here. The multiverse, whether real or not, has been a useful concept. It forces us to confront why our universe has its particular story. It encourages creativity in seeking answers, and it reminds us of the vast unknown that still surrounds our known island of reality. As the saying goes, the absence of evidence is not evidence of absence. We have no direct evidence for other universes, but neither do we have proof that our universe is the only one. We're like sailors on a lone ship, seeing a haze on the horizon that might be other ships, or might just be mirages. We train our instruments on it, we chart our theories, and we sail onward. In moving forward, we do so with both wonder and restraint. Wonder, because without it, we'd never have dared to think of parallel worlds or hidden dimensions. Restraint, because without it, we might mistake imagination for reality. The two in tandem are the hallmarks of science at its best. They allow us to dream, but also to wake up and check the dream against the world. So far, the dreams of multiverses live on, not confirmed, but also not dismissed, simply awaiting better tools or insights. They challenge us to refine what we mean by scientific proof, and how we handle questions that might always lie a bit beyond empirical reach. As we conclude this part of our journey beyond the universe, we find ourselves reflecting on our own universe with renewed appreciation. Even if it's one among billions, it is home. It obeys elegant laws, it spawned galaxies and stars, and at least one curious species that can contemplate the entirety of creation. Whether there's a grand cosmic multiverse or just a graceful lone cosmos, the quest to know what is out there and why things are this way is part of our nature. In the next part, we will continue that quest, keeping our feet on the ground even as our minds roam the heavens. There is more to explore, and as we venture on, we carry a simple dual lesson from this discussion. Stay curious, but also stay critical. The multiverse may or may not be real, but the spirit of investigation it inspires in us certainly is. And it is that spirit that will guide us, steady and bold, as our journey through the cosmos goes on.